technology.
Yeah.
What did he used to say? Easy things should be easy and hard things should be. Yeah, well,
Simple
apparently
things.
easy things are impossible.
Yeah.
I think that we are.
With this, you had this working 5 minutes ago, so
We could probably maybe we could use some old Engelbart equipment.
what?
It's going through. It's just really low. They just need to
We get the audio from the Zoom call. It's only a bit low.
So it was perfect when Ben was talking before.
Yeah, because I have.
Yeah, this is maxed out.
Okay, because it's better that you don't use this microphone.
That's fine. I won't use this microphone. I am happy to. I'll just turn it. You can make Alan audible.
Alan, try to speak.
People have been trying to shut me up for years.
Well, we finally succeeded, but now we can hear you. Yeah. So this is working.
Okay.
Finally.
Okay.
Yeah. So we're. You want to open my machine, or swap my or whatever? Hang on. It's in there, and yep, yeah, good. Now we just need to get you back on sound so that we can hear you. Say something.
Say something, please.
Hello there.
Okay.
Excellent. Okay, so please just don't touch anything. Okay, hang on. Yeah. Alan, we're swapping laptops for stupid reasons, and can you still see the audience, the room?
I can. I can even see Dan Ingalls.
Okay, yes, all right. So this is
One
working.
thing that happens when you get older, Gilad, is you reflect more light one way or another.
Yeah, okay. So I think we have the worst setup ever in terms of sort of audio visuals, but it's working. We don't yeah, do not breathe too strongly because something will fall.
I won't. Hey, how did your talk go, by the way? I heard there were internet problems.
Sorry, I didn't catch that because people are talking.
Because I knew your talk depended on the internet, and I was wondering.
Yeah, my talk depends very critically on the internet. So we actually do have good internet in the room, so that at least seems to work. And yeah, I was worried about the interview because we've had remote talks, as I told you, that have had problems because of the connection here. But now that aspect seems to be working, so let's hope it holds. And we will be. Now we have 7 minutes to spare. Unbelievable.
Hey,
But
that's great.
Anyway, thanks for.
Great to see you.
Sorry?
It's really great to see you.
Yeah, same here. Thanks for taking the time to talking to us. It's just right. I apologize. It's really loud here with all the people around.
Alan, can you hear me through this microphone? Alan, can you hear me through this microphone?
I don't think so. So Ben is trying to try another microphone and see if you can hear him through that, but it isn't working.
Can you hear me, Alan? Can you hear me?
Are you picking up anything from Ben?
So the room mic is not working.
Well, it's working in the room. No, this is just an attempt so that people, if people in the audience ask questions, we would like the mic to work, and you can, and it doesn't seem to. Yeah.
Can you hear me now, Alan?
Let's see. Get Dan to ask something.
Don't read my lips. Can you hear me now, Alan?
I can hear him laughing.
Yeah. Basically, he cannot hear you. Is the short answer. So I think what we'll need to do is I will have to repeat the questions. Yeah, because or they can yeah.
I think that will go on the live stream. So if people were on the live stream, have them turn my over the mic.
Oh, okay. So have them. So they will use the mic, and I will repeat for Alan. Okay. Just remind me of that. This is really flaky. Yeah. So what else can go wrong? It's all fine. I've never had more confidence in a setup than
Just don't break your own laptop.
yeah. Oh, and just yeah. The setup here, Alan, is yeah. There's a laptop I'm talking you through, and just above it is my laptop facing the audience. And all I need is to send my hand a little bit forward, and the whole thing will come crashing down.
Yes. Restrain yourself.
Yes. I should be handcuffed or something.
Yes.
But that's probably true in general.
As Larry David says, calm your enthusiasm.
Yes, exactly. I should be very, yeah. Maybe a Valium would help. Hey, yeah, come on over.
Hey, Alan, I just wanted to say hi before things get confusing.
Yes.
Great.
Yes, well, I'm going to say when we start that I should actually be interviewing you two guys. That's my opening line.
Yeah.
And I will if I run out of things to say.
Oh, I wouldn't worry. I have a list of questions a mile long. I could keep you busy for hours, but we're going to try and keep it manageable and give the audience a chance to ask questions as well. So.
Well, the number one thing with me is you have my full permission to shut me up as I run on, because I tend to run on.
Okay, we'll
you?
we'll try to manage time effectively and politely. But
Okay.
If I start waving hysterically, then
Yeah,
pause.
yeah, that's good.
I'm going to wander off and get a seat.
Okay,
Yeah.
great.
So 4 minutes to go. Most people will probably show up at just at the very last minute. Ben, so am I doing all Master of Ceremonies here for this session, or are you, Philip, want to say something about starting Rebase, any of that kind of? Just go for it. Okay. Hey. Good to see you.
So not to tempt the heavens, but at your end, you can record if you want.
I believe we are streaming and recording. Yeah.
Okay.
Yeah. No. You have no idea what we have done everything I think that we can, but. Okay, Alan, say something again.
Hello. Greetings from London.
Okay, is that going up? Okay, we upped your volume. Apparently, I am petrified of changing anything about this arrangement, but apparently that still works. Thank you.
It's like the good old days when computers would crash every hour or whenever they wanted.
Yeah, so, we now have, I don't know how many computers involved in this thing, 3 or 4, and
Yeah, so
one,
if we have
two,
enough
three,
going, and one should
4,
crash.
5, yeah. So we have 5 of them, and so, they have a good chance of contributing. Okay. Okay, we still have a minute or so to go. Okay.
This room looks set up so people can't sneak in from the back.
Yeah, they apparently have to come right across into the line of fire. So we'll get them if they come in late. We'll definitely.
We'll get them. Take names.
Yeah. Hey. Okay, we are.
Bingo.
Okay, it is 10:40, and we are going to start. Thank you, everyone, for coming to Rebase, and it is my great honor and privilege to be able to interview Alan Kay, who has graciously agreed to talk to us. Louder. Okay, louder. I apologize, Alan, if this comes in too loud for you. But yeah, nothing I said was important. The main point is we're starting, and where I have the privilege of interviewing Turing Award winner Alan Kay, the father of personal computing and all around a great guy. So this is the audio setup here is extremely fragile, so I'm gonna yell and hope that you can hear me, because if I put a microphone on, all hell breaks loose. So we're just gonna start, and I have a whole bunch of questions for Alan, and then people can put their questions into the Discord and or ask in the audience. We'll kind of intermingle these as we go along, but I'm going to kick this off. Alan is famous for these, I'd call them aphorisms, and one of them that especially I'm especially fond of, and I think would be useful, especially to younger people who are not familiar, as they should be, with Alan's work, is this idea that point of view is worth 80 IQ points. And I think, Alan, if you could explain what that means briefly, and also asking for a friend, how do you acquire these points of view?
Well, of course, I didn't specify the sign bit.
Yeah.
So that's the first thing to, the basic idea of an aphorism is it's a kind of lie that if it's done correctly, it points one's view in a positive direction. But if you try to take an aphorism apart, it quickly becomes ridiculous. So, but the basic idea, actually the basic idea behind aphorisms, because I don't think in terms of them, came about at Xerox PARC when we first had to learn how to communicate with Xerox executives. And at some point we realized they were not paragraph based. And I would call a lot of the people at Xerox PARC kind of paragraph. We liked whole paragraphs, not even sentences. And so the question is, what can you get across? And the answer is, well, proverbs. Proverbs are the shortest and earliest form of stories, and they have the ring of truth to them. So I started making up proverbs, and point of view is worth 80 IQ points is one of those. Trying to draw attention to the idea that every culture on the planet has accumulated lots of knowledge. One of my father was Australian. I grew up my first few years in Australia. My father was a great admirer of the indigenous Aborigine people in Australia. And he pointed out to me when I was a kid just how much they knew. And their point of view was different, but they could survive in the outback and we couldn't. And that made a big impression on me. And of course, I think anybody who's looked at the history of science, and particularly the transition from science as gathering knowledge to science as a collection of methods that in part try to get around the noisiness of our bad brains, realizes that these things called paradigm shifts could also be thought of as difference of points of view or differences in context or perspective. And boy, looking at something that's right in front of you with a different perspective can actually reveal things that are literally invisible to you, because our brains cannot see until we've learned how to see something. So this has been shown. So we have this improper notion that we actually see things out there, where in fact we learn things and the seeing is done inside, and it's often done in a faulty fashion. Yeah, so one of the problems with that aphorism is you have to relax and not do short-term thinking in order to use it, because the relaxation gets you out of your initial reactions to things. So this is what basically what current day AIs, so-called AIs, do wrong, is they react quickly and usually wrongly. So the real thing is to try and find ways of not reacting quick. I write things down in the notebook and then never look at them again. That way I feel like I've served my fast ideas in some way. I have many of these notebooks. I have no idea what's in them, but basically after a while you start having ideas from a different viewpoint. And sometimes those viewpoints can be really powerful. Often the viewpoints come from looking at, like, a big one for me was going from looking at simula, the first simula, as a better old thing to almost a new thing. So if you look at simula as a better old thing, you wind up eventually with something like C++, which is in fact the way C++ happened. Specifically, that's what Bjorn said in his first C++ paper. He was trying to do to C what the simula people did to algol. And you wind up with something like abstract data types. But if you take the other point of view is what if this is almost a new thing? So what it is transitional. What does that mean? And that will get you to a completely different set of thoughts.
So, Alan, one of the things you mentioned brings up another one of the questions I had, which I was going to save for later, but it's a good segue. You talked about LLMs. So, a commentary on the new wonder of the world and the AI situation. Yeah, maybe you can speak to that.
Well, I'll give you a parable. So in the 20s, actually in the early part of the 20th century, rays were a big deal, X-rays. So scientists looked for rays, and a scientist in France found the N-ray. And over a period of 15 years or so, more than 1,000 scientific papers. You can look this up in Wikipedia, by the way. More than 1,000 scientific papers were written about the N-ray. And then finally, several scientists proved that there was no N-ray. So, and so this is used actually by both sides. So people who don't like science say, look, science is just another belief system. Look at the N-ray. It has its fads and all this, and people who are for science, like I am, say, yes, but this fad only lasted for 15 years or so, and then the methods of science got rid of it. Try and do that to any religion that's around today. So you can look at these things in both ways, but basically human beings like to be right. We rationalize rather than think rationally. We have confirmation bias. We've got a billion ways of dealing with the bullshit that goes on in our heads. So the real question on any of these things, and I mean, another aphorism is the softer the science, the tougher you have to be. So if you're in a soft area, like if you're doing social science or you're doing something like so-called AI, you have to be really tough about it, because it allows our tendency towards theatrical thinking to intrude and impose our own beliefs and hopes on it, right? So I think it's really tough being a good scientist in the social sciences. And I think this is the case for the current setup. Now, that being said, if you look at Daniel Kahneman's book, Thinking Fast and Slow, you'll see in the beginning, he says, I have to tell you that I'm going to make use of two expository fictions. I love this phrase, expository. Expository fiction is a lie that helps you tell the truth. So it's like Picasso's definition of art. And Kahneman says, look, even if you take the billions of neurons in our brain and the trillions of connections and simplify them down to hundreds of modules, it's still too complicated to write a book about. So what I'm going to do is I'm going to call everything that results in a fast reaction, no matter where it is or where it came from, I'm going to call that system one. And he says it's not even a system. And I'm going to call everything that goes much more slowly, wherever it came from and wherever it is, I'm going to call it system two. And I'm going to see how much ground we can make with these two fictions at puzzling out some of the things that might be going on in our brain-mind conglomerate. And one way of looking at what happened is, in the early days, the people who were interested in what we now call, artificial I guess, artificial real AI or whatever, general AI. But in the early days, they looked more or less directly at the whole thing. And then there was the AI funding winter. And the thing that got popular was the lesser part of the problem, which is doing perceptron-like things with a few more layers. And the fact that Kohonen had showed that a form of matrix algebra was isomorphic to what perceptrons were made the papers look a lot more scientific than they actually were. And all of a sudden, you've got what academics really crave and academic funders like NSF really crave, which is the trappings of respectability. And I think, and it's not that, look, I have a stage 4 cancer. And the so-called AI, the stuff that isn't really AI, is actually helping me because it helps radiologists look at my PET scans every 3 months and try and figure out what new interesting source of sugar metabolism is going on besides all the stuff we can see from the brain and the bladder and so forth. So I'm happy for what the stuff can do. But I think everybody in computing should be unhappy for what is claimed. And if there's anything in the word science, if computer science is not a complete oxymoron, then scientific minds should be delineating what it can do and what it can't do. And smart people like Doug Lennett, who unfortunately left us last year, realized, well, what you want to do is, Kahneman's model is actually fairly good because we need correlators, whereas Judea Pearl calls them massive curve fitters. We need those because coincidence detection is the start of trying to find out whether the coincidences actually have any meaning. And so that's a good thing. But if you don't have the system too, to be careful about it, you're going to get what humans have had for a couple of 100,000 years, which is superstition and making up stories and all of these things. And so one way to think about it is just demand that the funders fund something more like a system that not only can propose things, but can also vet them. And I think given that any 12-year-old can set horrible things loose on the internet these days via free software, I think having some form of vetting system for almost anything that goes on the internet is actually a good idea. But I think that's out of the scope of this discussion.
Okay, awesome. So now I'm going to ask a question that I have to ask even if some people are less interested, but it's the perennial small talker question, right? Which is basically, why has Smalltalk not been as successful as small talkers think it should be? And do you think that's even a worthwhile question?
Oh.
No, I suspected that.
No, but of course, that won't keep me from giving you an answer.
Well, you could also, so my backup was, well, why isn't it a meaningful question? So you can, you answer whatever you want to answer to that.
Well, actually, I missed my chance to say at the beginning of this that I should be interviewing you, and I know Dan Ingalls is here. So me interviewing you two guys would be interesting also. And the complexities of which languages get chosen or not are sometimes even accidental. So I've never really actually tried to figure it out. But I think that part of the problem had to do that Smalltalk was successful, highly successful in the 70s. There was nothing like it in the 70s, but it was highly successful because Xerox PARC did what I think is the correct thing, which is it built hardware and software that work together. So we thought of whole system, the whole Xerox PARC, the ARPA community thought in terms of whole systems. And so it was not unusual to think of processes that would be really helpful and interesting, and to think of them in terms of some hardware-software combination. And PARC built all of its own hardware precisely because it did not want to try to do all the workarounds and even dead ends that were present in commercial software. And we were arrogant or confident enough, depending on how you look at it, to think that we could actually do hardware, and not just do it, but to do it in a timely enough fashion to allow the main enterprise at PARC to still be software. And that happened because of people like Chuck Thacker and Butler Lampson, and a lot of stuff happened. But basically, we wound up being able to make the equivalent of a supercomputer for each person at PARC, including all the secretaries and so forth. And because of the way the microcode engine on this machine was designed, and purposely, because we knew we were going to be doing virtual machines of various kinds on it, we could actually make the equivalent of custom hardware before the fact. And, you know, there's a lot of history that goes behind this desire. Part of it, as you know, as well as I do, goes back all the way back to the Burroughs B5000. And it's the fact that it was a byte encoded virtual machine in hardware. And it was a more general machine than either Algol 58 or Algol 60. It was more like a Simula machine before Simula happened. So it was a genius level thing. And the one lesson to be learned from it, besides the fact that this is a good way to do things, is that microcode really would have helped the B5000. And of course, Bob Barton, who was the designer of it, the next thing he did after the B5500 actually was microcode. I think that was called the Burroughs 1700 or something like that, because basically in order to deal with learning curves, you need to have some wiggle room in the lowest level of the machine. And the Burroughs B5000 was wonderful for what it was designed for, but didn't have enough wiggle room. So with these microcode engines, which were a great idea for their time, like today you would use something like field programmable gate arrays that would plug into you know, blade servers or something like that to allow you to make a synthesis, and you would have languages that would allow you to program all the way down to the actual gate level if you needed to, because why not?
Okay, now I have, at some point we'll bring in the audience, but I have one question that I don't want to miss, which is sort of a larger question, and that is, looking back, what would you have done different than, you know, in terms of your career, and you've had a huge impact and so forth, what are the things that you might have approached differently or done differently?
Well, you know, I like John Lennon had a great comment, which is life is what happens while you're making plans. So if I will never write a memoir, but if I were to, it would be called something like An Accidental Life. I never wound up making a plan. It was like a leaf on a stream going down, turning around, and occasionally bumping up against shore, and there were interesting things, and then back on the leaf again. So I wouldn't change my plans since I didn't have any, but I did learn a few things. A couple of them I should have known. So, but I think one thing that's hard for any kind of funder today to actually appreciate is what the word research actually means. And in an aphorism, research means you can change your mind. So whatever goal there is to turn up something new and interesting. Bell Labs had signs This is back before the divestiture, but you sign on a stairwell or sign on a wall that said, either do something really beautiful or really useful. That was what the sign said. And the people who funded Bell Labs did not care which. They wanted something extreme, and it could be in one direction or the other. They didn't care. So a lot of good things came out of people following their nose. And some people had the nose for practicality, and some people had the nose for beauty, and some people had both. So I think that, but the one thing I came to appreciate about Park, and particularly our group at Park, is the thing is, if you're going to have a group, you might as well have the best people. So you basically want to have people that are better than you are. Because if you can be friends, drink enough beer together, basically, you might be able to synergize these different talents. And that fact, if you get synergy, is going to give you something. It may not be what you originally thought you were out after, but it can give you something that is really, really interesting. So you mentioned Smalltalk. So it is certainly one of the most interesting computer artifacts done in the 20th century. It stands out even today in many different ways. And so I think one way to think about these interesting artifacts are similar to the way I think about the first Simula, which was, it wasn't that it was perfect and the first Simula didn't really succeed either. We could ask, why didn't Simula make it, especially Simula 67? It was pretty darn good. And it was really, on the other hand, it was really early. It had all of these different barriers that we're used to coming up against. But I think that if you're doing your job right and you're actually doing research, you're creating things that have enough integrity and interest to still be mentioned, as we are doing right now, more than 50 years after the fact. Right? I'm being asked the question about Smalltalk, and the guy who made it really possible is sitting in this room. So we should follow up by asking him. But the realization I had some years later as a research leader is, if your strength is starting things and you're partially looking for completers to get the thing done, let them complete. Right? If you have more ideas, go and start another group. Don't try and dissuade because completers have their own dynamics, their own sense of aesthetics. And I didn't realize that at an early enough point. And it turned out that it was good that they completed, because the actual insights needed to have the first success, stuff that I considered successful with children, didn't happen until about 25 years later. It wasn't until Disney in the late 90s that, and this is your point of view is worth 80 IQ points idea, I realized I had actually gotten sucked into my own Kool-Aid. Because mathematical background, it's nice. Math is really nice to build entire universes from tiny little universal principles and stuff. And Smalltalk is certainly an interesting example of that. The thing that worked with the kids was actually the opposite idea. It's not the way mathematicians think of it, but more the way scientists think of something like Maxwell's equations, where you basically, you have, you can put it on a t-shirt, but it is a pretty complex combination of powers. But the power of it is, once you have the t-shirt, pretty much everything else in the electromagnetic realm is just parametric. And so the thing that worked for a children's language was to give them, instead of a minimal object that you build everything out of, which was not in the children's space, was instead to give them one universal object in which everything interesting was parametric. And there are a few other ideas in there, but I was struck by how opposite the two ideas actually were. And of course, thanks to Dan and Smalltalk and Squeak, we had Smalltalk and Squeak to do this different set of ideas on, and so it rode on top of Squeak Smalltalk. So the whole story had a happy ending from my point of view.
Happy endings are good. Maybe people are...
It helps if you're happy.
That's true. That's point of view again. But do we have audience questions? Because people might be tired of me asking questions. Otherwise, I can go on forever, but yeah. Okay, so the logistics here are very tricky. You need the microphone so it goes to the stream and the recording. But then I need to repeat the question for Alan because the microphone doesn't go to his audio, and so we just have to get this right. So, oh, you've got it in writing. Okay, where is it? It is this one. Okay, we are still talking about Smalltalk and Simula today. Does this indicate that these ideas and artifacts have integrity, or they are just very compelling superstitions? Oh, I like that. How can we tell the difference?
Yeah. Well, look, on questions like this, it's sometimes good to go to neutral ground. Like, what kind of scaling has happened over the last 50 years? What programming language has survived the scalings of Moore's law? And if you look at the scalings of Moore's law in hardware, it's happened mostly by not inventing new good hardware architectures, but by recapitulating old architectures, basically doing away with a couple of levels of design that really are needed in order to just get the design rules a few nanometers smaller. So, but if you apply the scaling that's happened to programming languages, the shocking thing is that any programming language, Smalltalk or not, done back in the late 70s or early 80s is still being programmed in today. And in fact, it's shocking to me that hardly, at least from the outside, I don't consider myself an insider anymore, but from the outside, the progress in programming language design looks to be close to nil. And that is completely different from the 60s and 70s, where paradigmatic shifts in the ways of thinking about programming were happening every 5 or 10 years or so. And what's happened since then has been way too much optimization, to me, of the wrong kind. So I would expect, for example, not to ever see the news that we got from CrowdStrike. What a terrible name for a company. Worthy of George Orwell. But how could that happen? Or Facebook taking itself off the internet, including its own computers, for more than a day, because its 9,000 unit tests did not include one that said, hey, our main large goal is to be on the internet and serving people. Or an ominous one like the Boeing 737 MAX autopilot that crashed 2 planes full of living people into the ground because of some bad decisions of management and engineers going along with it. So, I mean, I would expect to see software that is actually primarily set up, let's let's take another analogy to the Hippocratic Oath. In the middle of that is the phrase, above all, do no harm. So that's the main admonition for doctors. And of course, they've done a lot of harm over the years, but they're, in theory, trying not to. But for engineers, the equivalent of that is the bridge must not fall, the building must not cave in, the airplane must not crash. And we don't have one for software, which should say something like the system should be safe, the system should not hurt people. And I don't know of much, if any, software that is wrapped with the checks and balances before actual actions in the outside world can be done. And I would expect this, and one of the many things I learned from Butler Lamson years ago is that if you're interested in security and safety, don't try and bolt it onto your system afterwards. And this is like the same principle for user interface. If this thing is eventually going to be used by a human, start off with a user interface, because it is really hard to put a good user interface on sheer functionality after the fact. This accounts for most of the bad user interfaces in the world today. So, just as an outsider now, things look completely ass backwards to me, and they don't take into account either the scale or the reach in both time and space. For instance, should the stock market be allowed to do lightning trades at the rate it is allowed to do? As a systems guy, I would say absolutely not. Part of the stability of the stock market and the way it actually worked depended on this thing called the float, which had to do with the time for messages to get through the system. If you change the message rate in a system, you're going to change how the system responds to various kinds of stresses. So yeah, so the reason I didn't have a direct answer for Smalltalk is, I love what we did back then, but a lot of the things we did back then were, in anticipation of some of the scalings that would come ahead. But if, as as somebody who's used Smalltalk, we could have made the interior of an object much more like a real world. And we didn't, because we didn't have enough space. We resolved to be careful about how we did various kinds of things. And we got around things and still came up with some elegant looking and working software. But as you expand outwards, you start getting into problems like, for instance, putting labels on things gets less and less useful as you expand out onto the internet. You want to find things by descriptions and by matching descriptions and matching behaviors rather than trying to match up names. So the whole idea of interfaces actually has to be different. You need something perhaps more like what Galerner was trying to do with Linda, right? And what you would do there was to try and understand exactly how you're going to deal with semantics that you can recognize but don't have a name for. And like another thing you could do, just as an example, is you could say, here's an object that is going to be very helpful, but it makes use of global resources. So the worst thing you could possibly do is have a variable to stand for those global resources, right? Because what you really want is to stick an object in each one of those variables whose job it is to first imitate the global resource, so you can debug your main object. But it can also, when you ship the object off, it can also adjudicate with what the global resource is trying to link you up to. So these are just elementary system ideas that arise when you think about what are the actual problems of scaling. And I would love somebody to show me a system that does even these simple things rather than showing me millions of lines of very, very rickety code.
So
I'd like to see, yes.
I wanted to latch into one of the things you said when you talked about safety, and there are a lot of people here who are concerned with safety and verification, and I cannot resist the temptation to ask you to comment on functional programming, because
Yeah, well,
that is a lot of what that community is about.
But remember, do you remember what Gandhi said when they asked him what he thought about Western civilization? He said he thought it would be a good idea.
Yes, it was worth asking you that.
Yeah. So, I've answered this question a few times in Quora, but to me, the real idea about thinking in terms of functional relationships. So let's not use the FP term, but in thinking about terms of functional relationships, it means that you can reason from what John McCarthy called a situation back in the late 50s, from one set of states to the next set of states. That was what he wanted when he was trying to do this software interface called the advice taker. And it was the desire to make this advice taker that caused him to invent Lisp as a programming language to program the advice taker in. And in both cases, McCarthy realized that you had to deal, in his terms, because he was a mathematician and a logician, he would have to use something like a modal logic in order to reason about things happening in the real world, namely that, like on Monday, the robot is in Philadelphia, and on Tuesday, it's in Boston. And he realized that unless you included a timestamp for any fact, and that gives you a modal logic, gives you a temporal logic, you can't actually reason about most interesting things in a computing system, because the whole idea is to get state to change and evolve over time. So McCarthy called what today we would call a world, he called it a situation, and he called these pseudo timestamps fluents. So this is back before the tyranny of semaphores and monitors, and this is a really great set of ideas, because basically what McCarthy was saying, look, what we were doing on the computer is simulating models. And the thing we're basically doing wrong is we're letting the CPU tell us what time it is. And what we want to do is we should simulate time also. We'll use pseudo time. And by the way, the first Simula did this. The way Simula scheduled its processes was what it called a scheduling set. And the scheduling set, each process in this set of things to be scheduled was marked with a pseudo time when it was supposed to happen. And the way Simula worked was when it would get done with the actions for a particular time, the next thing in the scheduling set was the next actual time. So it just immediately go to that time. And so it computed in between time changes. So this is a great idea. And Simula 1 actually had a predicate that would tell you if somebody else was scheduled for the same pseudo time you were in. Yeah, because that would allow,
yeah, go ahead.
right? So Yeah, so this, uh, what McCarthy was able to achieve here was a way to think about functional programming in a much stronger way than most of the thoughts since then, which are way too much like regular mathematics. So McCarthy's idea was you have a situation, which is a set of stable stuff, and you can reason about it. And by the way, you can use it to make your next stable situation. And if the mapping between situation one and situation two can actually be functional, because you can have, with pseudotime, you don't have any race conditions unless you permit them. And so McCarthy was thinking about, and when you throw objects in, you basically think of a sea of objects that, if they can really send messages to each other, they are actually compatible. And in an ideal system, you would actually be moving the sea of objects from one stable situation to the next stable situation. So this is in keeping with some of the ideas that were done with databases and transactions, but it's applying it to whole systems. That if you can think of terms of, then you actually wind up with something where you're making a model. You don't have to use distortions of an idea like monads in order to do. You have state changing, but the state is changing the way it does, say, in a bank account. No race conditions are allowed on a bank account, and things are set up so that at any given time, you can do accounting on your file structure across all the files, and just exactly what it is. And the thing that's the problem in programming language is that I think people don't really understand objects very well, because they're still thinking of them as being data on the one hand and process on the other. And you really have to link them together in a stronger way. And then you get a functional programming that is absolutely functional, absolutely can be reasoned about, and would be a lot of work. But for instance, Alex Worth, who I think gave a talk on Monday, and Yoshiki did a system called Worlds. Yoshiki Oshima did a system called Worlds, which tries to show how you can deal with various forms of undo at different timescales. So if you think of this idea of going back down through the world lines, how much of the past should you retain? What does it mean to go back? And so forth. And the grain size of things, it means it's going to be like sorting, where you have different methods for sorting a few things and different methods for sorting large things. The predicate for sorting is the same. And the same idea for functional programming. You have basically a predicate for what it actually means to move from one state to another in a graceful way.
Cool. I was looking for a definition for monad for years. Thank you for that. I think we probably have other audience stuff, right? We should
probably do it.
Oh, from the audience? Yeah, however we want to do it. So a reminder again, microphone, and then I have to repeat the question. So questions from the audience. I don't think it's doing much. It's not doing much.
Can you press it once more?
Hi, Alan.
Can you hear any of that? I'll repeat it anyway.
Okay. How much of this lack of progress that you lament has to do with learning difficult to learn things? As you said, the future of reading depends on the future of learning difficult to learn things. So how do we learn difficult to learn things in order to make progress?
Okay, I'll try and repeat that.
Oh, I got
you got it?
that.
Okay, excellent.
Got it. Yeah, so that was a paper I wrote for a book, chapter in a book years ago about the future of reading. And the title was "The Future of Reading is the Future of learning to learn difficult to learn things. So, meaning what reading and writing is about, in being serious about it, is having something interesting to write about that's then interesting to read about. And one of the ideas from back in the 60s was that the computers were going to give us an additional way to represent complex things like dynamic systems, processes, representing communication systems and so forth. And that the media for writing about this had to include, like right now when I write something on Quora, I can write in words, or Wikipedia, I write in words, I can stick in a picture, maybe stick in a movie, but I can't stick in a computer example, even though people are reading Quora on a computer. So if you want a definition of nuts, this is even better than Einstein's idea of crazy is doing the same thing over and over again and expecting something different. I mean, it is literally crazy to be confined to old media when you're on something new that has new ideas that need to be experienced in order to be understood. So it's very, very difficult to actually write about computing in computer terms, right? So that's a simple idea from it, and that's one of my biggest complaints. So to try and answer the question, I'm afraid I think one of the, and this is an old fogey reaction, but I think one of the problems that seemed to be pretty apparent when I was doing some teaching at UCLA to both undergraduates and graduates was, wow, what a terrible waste of these kids' lives to have an undergraduate degree in computing. Because think about what they could actually be learning if they weren't taking up all this time learning almost nothing interesting. And that learning they would do would actually make them much more sensitive to the new things they could be learning about. And of course, that's not the whole story, because let's face it, things are very different than they were in the 60s and 70s, especially with regard to life-affecting things like, for instance, real estate prices, which are not counted in inflation, and in California have been more than a factor of 10 over regular inflation. And this has changed the goal structure of lots of kids going to college. And they're not getting much in high school. So college is doing a lot of the work that high school used to do. And because of this vocationalism, it is not doing what college used to do, which is to be the keepers of the flame of ideas, of what it means to be involved in ideas and making ideas and thinking about ideas, and above all, criticizing ideas. So one of the things I used to do in my classes, and if I were here present, I would try to get people in the crowd to really criticize the web and the web browser. It is really hard for undergraduates. They're trying to learn it. They're not trying to criticize. It's crap. It's one of the worst set of things ever done. It set us back 20 years. Yeah, in fact, 20 years ago, I used to complain about not being able to do WYSIWYG editing. And people would say, well, it's, we're working on it. And we still don't have it. Like, for goodness sakes, come on. It only took a few years to invent it in the first place. Why is it so hard to do? So this is a little bit like the difficulty the US is having getting back out into space. A lot happened in a few years, and some combination of the will and the zeitgeist and funding and everything else has made it extremely difficult to get to the next stages. Yeah, so I think that question that was asked, I think it's the best question I've been asked in a long time, because I think in order to move forward, we somehow have to be able to criticize, even as we love, like, I love Lisp. I had nothing to do with it, but the hours that I spent one afternoon actually going through the eval and understanding it were transformative, because it basically took a lot of ideas and made them down into this little eyeful and a brainful. And all of a sudden it was easier to think about many different things. Now, I've had that happen a number of times, but I would never program in Lisp today, because even as I love it, it is a wonderful thing from the past. Same thing with Smalltalk. So, so one of the things that the universities, I think, are missing in their prime job, which used to be not only learning about what has been done in the past, but learning how to critique the past. And I don't see that spirit, certainly in the engineering schools. I think that is a disaster. And I personally don't think universities should be trade schools. Or if they are going to be trade schools, then they should have a separate department for teaching the trade of dealing with legacy programming and business. That's a perfectly reasonable trade, but I don't think it has anything to do with making computer science move ahead.
Cool. I guess we have time for probably one more.
I see a hand down there in front.
Yeah. They're working on the microphone.
So far, yes.
Or just come up here. If
No?
come here
Okay.
and just say it here. That's simpler.
Hey, Alan, do you think that there's a limit to the amount of progress we could make? Certainly, a lot of things that were common 50 years ago, or the things that were pushing the boundaries 50 years ago are becoming common: memory management, databases, everything. But has it taken this long to really absorb as a society, or do you think we could make that explosive progress that we saw early on?
Well, I think what's in between our ears is definitely finite. And I think our powers of abstraction are almost certainly finite. But it's like saying, asking, is science the final answer? And my answer to that question is, well, it doesn't matter, because the answers we're getting from science are very, very helpful and illuminating. So let's keep on with it. I think I don't want to point. I hate to criticize without really backing it up, but certainly I think the easy commercialization that happened in personal computing in the 80s, which is a particularly tough time for languages like Lisp and Smalltalk, because you're all of a sudden you're going to something that, like a processor that's going to like something like C much more than something like Lisp or Smalltalk. And you're also in a position where something like Unix was starting to be used in universities. So right away you have, the reason we used emitter coupled logic at Park was the micro engines had to be fast in order to predict into the compute into the future like we did. And this intermediate period where we had 8-bit micros and then slow 16-bit micros that could be put into machines like the Apple II and then the Macintosh, but without the amount of bang for the buck that the higher level software needed. I think if you were to go back and look at this, it actually created a desperate problem for people who are interested in higher level languages. Now, to some extent, people like Peter Deutsch and you mitigated that by finding various ways like just-in-time compilation to deal and there's tracing optimization and so forth. There's ways of dealing with a bad processor and a very high level language if you have enough memory for caching. But I think there was a huge mismatch there that effectively, you had to, for doing Lisp, there was a board that you could, on a cable, you could plug into an IBM PC that would do what Lisp did slowly but well. And so I think what happened is normal got redefined in the 80s. And from most people's standpoint, it got redefined upwards because all of a sudden there are personal computers. I think from the standpoint of the people who were working on a very large vision like the one that Park had, normal got redefined downwards. It was like going back in time 100 years to come out of Park and into the general world there. And I don't think and you could sell them. So all of a sudden marketing people got involved, and marketing people hate learning curves. So the tendency was, what can we sell that doesn't have a learning curve, that is worth something to somebody who has some extra bucks out there? Well, why not sell conveniences? And we could sell video games. Those are two things that are really built in. Conveniences, people are already reading and writing. Let's sell word processors. And so you basically have this marketing level that didn't look ahead towards any new media. We're using a medium today in Zoom that does less functionally than what Engelbart's mother of all demos did in 1968. Because we cannot share the way Engelbart had sharing by multiple people of multiple things built into the operating system. I don't know of any of the regular operating systems today that has that even today. So I feel that what happened was things moved into a comfortable area of consumer electronics and toys. And that the education system, as usual, lagged way behind. And because it lagged way behind, what it decided to do is to teach the bad designs that were being sold to consumers, because that's what were out there. And so you got this perpetual motion fur farm, which, you know what that is.
So that is the perfect note to end this session. Thank you so much, Alan. This was terrific. I could go on for a long time, but
let us all give Dan Ingalls a cheer.
Absolutely.
Because he was one of these people who absolutely went after what was just barely possible, and you were also, Gilad. Going after what's just barely possible that qualitatively changes things is how we get ahead. That's what we need to teach kids in school.
Thank you. Again, awesome. Thanks everyone for attending. Okay, take care.
Bye-bye.
Bye. Okay. Whose computer? This is mine. Okay. Wow, it's like a dongle factory over here. Oh, that's cool. It's like a universal everything dongle for your Mac. Okay. Yeah, whatever. Whoa. Hello, hello. Is this, check it out. Oh, it's doing it. It's doing it. All right. Okay, sounds good. I'm just gonna go use the restroom. Oh, I was just, whatever. Hey everybody, I'm Phil, and I'll tell you about Fil-C. So, what is Fil-C? So Fil-C is a memory-safe language with absolutely no escape hatches. It's not like the fake memory safety of like Rust, where you can say unsafe anytime you want. There's no unsafe escape hatch. So the rules of Fil-C are always upheld. And it's safe to the point that you can't even link to unsafe libraries. So even the libc and libc++ are memory safe. And it's insanely compatible with C and C++. So
Lots of programs compile with Fil-C with no changes, and then a whole bunch of programs compile with like reasonable or minimal changes. CPython, for example, works with, I think, like a 50 kilobyte patch to CPython. I'm working on performance. It started out being like 200x slower. Right now, it's 1.5x slower in like the good cases, 5x slower in the not so good cases. But I'm like on a trajectory where it's getting faster and faster all the time. So agenda for the talk, I'm gonna start with the demo because I just wanna lay the groundwork to show you that this is like a real thing. And then I'll talk about the goals, and then just a quick review of previous results, the key insights that make the thing work, and just a summary of the results, I guess. All right, demo. Let's do a demo. So, Fil-C, currently I'm developing it on my Linux box, Linux x86-64. There's nothing fundamental about it that's tied to Linux on x86-64. I just wanted to have something that I'm developing on. So to start off the demo, to make it really fun, instead of using the shell that comes with Linux, I'm going to start a shell that I compiled with Fil-C. So this is the Z shell compiled with Fil-C. So the entire Z shell source code compiled with Fil-C running on top of musl compiled with Fil-C. So no memory unsafe code going on in there at all. Whoa, hey, look, I managed to make it crash with a memory safety error. Let's try that again. So, I mean, obviously, whoops, let's, you can see it's like it's, apparently on this computer, when I press tab, it triggers something in there that doesn't work. So you can see when it crashes, you get a stack trace, and that's a really deep stack trace. And it's reading an out-of-bounds pointer somewhere in meta char len conv. Maybe that's an actual memory safety error in Z shell, or maybe it's just like it's doing some C thing that I haven't handled yet. But whatever, we're gonna keep going with the demo. So in here, what I've got is I've got the URL for xzutils, and we're gonna git clone xzutils. This is gonna be spicy because, I mean, it's a live Git repo. They could have changed it. So I'm just gonna clone it. Git itself, I haven't compiled with Fil-C. I'm gonna try to remember not to press tab. For some reason on my computer, on my other computer, when I press tab, Z shell is fine, so whatever, I'll debug it later. So we've cloned xz, or remember not to press tab. You can see that I'm running the omyzsh extension to Z shell, which further stresses it. So there's a whole bunch of code in Z shell that's interpreting this complex script that gives it all this styling, including the fact that it now knows that I'm in a Git directory and whatever. So here's how you port a piece of software to Fil-C. Well, first of all, since I've checked this out from, that time pressing tab worked, good for me. So I'm gonna run the autogen script, because you have to run the autogen script to get the configure script, as we all know. So now that I've got the configure script, to get this to compile with Fil-C, I'm just going to point it, oh good, tab is working now, I'm so thankful. Bin Clang, so this is my version of Clang. It's based on Clang 17, and then I'm just gonna do configure. So now you're seeing like multiple levels of demo of Fil-C. We're running a shell that's compiled in Fil-C, and then the configure script, what it's doing is it's compiling stuff with my compiler and then running it to test if it all works, to figure out what features are going on and whatever. So we've already compiled and run a bunch of Fil-C programs, but now let's get real and let's compile xzutils with Fil-C. So you can see that it's using the libtool thing to invoke my version of Clang. And let's see, it's probably already done compiling. Is it? It's almost done. Oh, come on, scroll down. There we go. Okay, cool. So we've compiled xzutils. And I'm going to use this xzutils that I compiled to compress libpslow, the runtime for Fil-C. So src xz libpslow.so. Let's see if this works. If you think it's slow, I'll show you how much slower it is than normal xz in a minute. So it compressed it. Fantastic. No memory safety errors. That's great. And then we're going to decompress it. Oh, no, look at that. So I'm familiar with this bug. Basically, there's a part in XZutils on the decompression side where it uses inline assembly. When I say no escape hatches, I mean it. I don't allow inline assembly. Also, if you pass an out-of-line assembly file to my compiler will crash with an error. So now we're going to fix this bug, and we're going to fix it just to make it extra fun. We're going to fix it using a version of the MG editor. MG is an Emacs clone that I compiled with Fil-C. MG actually compiles and runs with no changes. Really cool. So I remember exactly where this thing is. liblzma, range decoder.h. Okay, so here you go. We're editing a text file in a memory-safe text editor. It's written in C, but it's totally memory-safe. And the issue is that in this header, it's got some macros that will either use x86-64 assembly or just C to do some stuff. So the way you detect if you're in Fil-C, this is my personal project, so I get to make stuff up. It's Pislinator was here. All right. So if not defined, did I spell that right? Pislinator was here. Cool, I spelled it right. So you can see Z Shell's process management is working. This is important because Fil-C has memory-safe signal handling and memory-safe fork. So it's not just C, but all of the universe of stuff that a C programmer on POSIX would expect works in Fil-C, and there's no escape from it. I won't have time in this talk to tell you how I made signal handling memory safe, but I did. So now we remake it so that we get a new version of it that doesn't have that particular bug. And there it is. So now we can try to decompress again. It's going to complain because when it last tried to, it already created the libpslo.so file, but didn't actually write anything to it. So now we decompress it. You can see that was pretty fast. So now let's look at how fast it is relative to normal XZ. So we're going to time compressing libpslo. You can see compressing with XZ is actually, it takes some time. It's like a sophisticated compression algorithm. So that's how long it takes. So 2.96 seconds to compress and 0.17 seconds to decompress if you're just using the normal stock XZ compiled with a normal C compiler. But the one compiled by me, let's see how long that takes. So we're gonna time. Whoops, it's not .xz. Let's actually use the right file name. So to compress libpslo with XZ takes 5.51 seconds, and then to decompress takes 0.26 seconds. Now I don't want to do the math in my head of what the overhead is. So what I'm going to do is I'm going to launch CPython compiled with Fil-C in order to use its REPL to do the math. So this is memory-safe Python. What's really cool about this is Python's huge and has its own garbage collector, does all kinds of crazy stuff. It even uses shared memory IPC for parallelism during its install process. So this is a properly make installed Python that's compiled all of its bytecode using this. Because they don't have real threads, so they have to use multiple processes in shared memory IPC. And shared memory in Fil-C works and is also memory safe. So yeah. All right, so there we go. We're in a REPL. You can see it popped into the REPL very quickly because Python in Fil-C is not super slow or anything. It's reasonable performance Python, and it's all totally memory safe. So on the compression side, it was 1.86 times slower, so less than 2x slower than normal C. And then on the decompression side, it was 0.17, so about 1.5x slower. So in the good cases, 1.5x slowdown. In the bad cases, bigger slowdown. That's where I am today. Not guaranteed that I'll be there tomorrow because I keep making it faster. You can see that job control just works. It knows that there's a suspended job. I can FG, then it sees that it was killed, and I can kill the shell. So yeah, so that's the demo. That's Fil-C like actually working for realsies. So now let me get back to my keynote deck. All right, so let me talk about goals. Like, what am I trying to do here? These are the goals in descending order of importance. The first is, so I could have just said memory safety, but I can't do that anymore because people are using the term memory safety to mean completely ridiculous things that aren't memory safety. For example, a lot of languages are memory safe but have an unsafe escape hatch that you have to use to be productive. Rust, I'm looking at you. I even saw a thing where someone was claiming that Delphi is memory safe, even though Delphi has manual memory management that's totally not safe. So like, people are throwing around memory safety almost like if it's not C, then it's memory safe. So here's what I mean by memory safety. I come from a background of implementing JavaScript VMs and Java VMs. In JavaScript or Java, it's like any sequence of characters fed to the implementation will result in a memory safe outcome. And if it doesn't, it's like a priority 1 bug that the implementers will fix. So what I call this GIMSO, garbage in, memory safety out. So the rules that the language is upholding are upheld even under adversarial input. So the goal here is that if you get the Fil-C version of Clang to compile your C code, then that C code cannot escape out of Fil-C's protections. And those protections are meant to be meaningful from a security standpoint. So WebAssembly you can think of as being memory safe, but in WebAssembly you can do basically data-only attacks which are just as dangerous as remote code execution. You can go out of bounds of an array and start overwriting somebody else's array. In Fil-C, we protect bounds, pointer integer type confusion, and use after free. Those are the big ones. And there's other stuff, but those are the really critical things. Bounds, pointer integer type confusion, and use after free. The next goal, which is almost as important, is compatibility with C and C++. I'm aiming for maximal compatibility to the point that, like you saw in my demo, I can run a configure script that I checked out from GitHub, just pointed at my compiler, and things basically work. That goal is secondary to GIMSO because if there's ever a contest between GIMSO and compatibility, I pick GIMSO. For example, I don't allow inline assembly even though I could. If I did, it would make me more compatible but less safe. Also, this is not a new compiler for C. This is Clang, and I'm aiming for a minimal change to Clang and LLVM. Just so like all of the good stuff in Clang that you expect to get as a Clang user still mostly works. So like, for example, I can compile Daniel Lemayere's SIMD UTF library and run it just fine because since I am Clang, I have all the Clang SIMD intrinsics that Lemire loves to use, and they just work. And finally, reasonable performance. I deliberately put that one last. You know, if I was doing this to try to get a paper at PLDI, then I'd have to put that one up here. But I'm not. So I'm going for something. To me, I think it's an interesting intellectual outcome if I can make the C language, like if I can make an implementation of the C language that's compatible and completely memory safe, even if it is super slow. So performance is like, it's not a non-goal, but it's the least important of these goals. But I did specifically pick a non-goal very deliberately, and that's binary compatibility with YOLO C. That's what I call like normal C. So if you hear me say YOLO C, that's regular C. This is a non-goal that I picked primarily because the pointy-haired boss in me wanted to like have a scope reduction to make this like project realistic. But it's actually also kind of an asset that I have this as a non-goal, because if I had ABI compatibility with YOLO C, then it would incentivize me and other users to say, okay, I'm gonna recompile this file with Fil-C, link it to a whole bunch of files that are normal C because I don't wanna be bothered with porting them. And then what you'll get as a result is a program that is not memory safe. I think that in order to get a memory safe process, like the thing that makes like Java or JavaScript or TypeScript memory safe is that substantially all of the stuff in there is memory safe, not that like 10% of it is or something like that. So not having ABI compatibility is kind of an asset. And guess what? If you want to link against somebody's C library in Fil-C, you can just recompile it in Fil-C because it's so compatible. All right, so previous results. part of the reason why I was motivated to do this is that this is kind of like a scoured territory of solved problem. Like, there's so many approaches that people have tried to make C memory safe, and so many of them were substantially successful. But if you add the GIMSO goal, then a lot of them fall off. Softbound and effective SAN both got really close, but they didn't handle corner cases of the language. Things like checked C and circle and F-bound safety are like opt-ins. In the case of checked C and F-bound safety, they only handle spatial safety, so type confusion use after free is not handled at all. ASAN MTE is probabilistic. WASM RLBox native client, they give you a sandbox, but they don't actually make the code running in that sandbox memory safe. So most of these don't actually give you the GIMSO goal. And then if you want maximal compatibility, then Safe C, JNK, they couldn't even handle C++. Cyclone's a completely new language. C-cured required that you write your mallocs in a very idiomatic way. And that's if you use their static analysis to convert to the real C-cured, which actually was a different language. So that kind of leaves Cherry. Is this showing me the, oh, this is like, I'm one slide behind on this or something. Oh, there we go. I hope I wasn't one slide behind the whole time. That leaves Cherry, but I actually think that Cherry isn't really compatible because it's whole new hardware. I wouldn't be able to run Cherry for you in a demo unless I ran it in QEMU or some IoT device that's hard to get. And if I did, it would be a lot slower than Fil-C is in practice because I would be running either in an emulator or on a really bad CPU. So Cherry succeeds at like source compatibility literally, but fails at the other kind of compatibility, which is can I run it on like the computer that I actually have. All right, so key insights. So nobody's achieved those two like top goals that I have, which is compatibility and GIMSO. So that's what makes Fil-C new, is that I actually tried to go there. But I would point out that like this work wouldn't have happened if it wasn't for all of these past attempts. Fil-C takes massive inspiration from C-cured and from softbound and effective SAN. So, you know, it's cool that people did this research. So here are the key insights of Fil-C. First of all, I'm just going all in on garbage collection, and I'll tell you why. It's actually really great. It's my favorite part of this, is that it's garbage collected. The fact that it's garbage collected enables the capability model, which then gives me that maximum compatibility. The capability model is called monocaps. It's a novel capability model for C. If you read the literature on memory safe Cs, the way that one paper distinguishes itself from another is the capability model. This is a completely new capability model that I'll be telling you about. And then I'll tell you about the runtime, which is what I call the libc sandwich. And then finally, I'll tell you about how just a little bit about how I achieve GIMSO and LLVM. So garbage collection. It's like my own garbage collection algorithm. It's accurate, concurrent, non-moving. I could probably do a whole talk on the GC algorithm itself. If you're familiar with the Dolly-Gay-Lavoie-Gonthier concurrent GC, it's sort of like that, except has a cheaper barrier. It's an algorithm I've used before. I have high confidence that it's decent. And it's definitely not the longest pole in the tent in terms of performance. That 1.5x slowdown you saw in XZ was not due to the garbage collector. It was due to everything else. So why have a garbage collector? The first reason is that it gives me a deterministic answer to what happens on use after free. A lot of these other approaches to memory safety in C kind of throw their hands up in the air for use after free. Like, you can use after free in softbound. You can use after free in effective SAN. You cannot use after free in Fil-C. And then the other thing that it gives me is that it gives me these monotonic capabilities. So what the hell are monotonic capabilities? So if you're passing around a pointer in Fil-C, you're passing around a 128-bit thing, and 64 of those bits are totally under your control. The raw pointer is totally under your control. You can use pointer arithmetic to make it point anywhere in memory, including out of bounds of whatever object it's supposed to be pointing at. The other 64 bits are not under your control, but they are carried with the pointer as you pass it around. And those other 64 bits point at a GC allocated capability object that describes where the raw pointer could dereference what. So here's what it looks like. Gosh, okay, there we go. I was worried that I was one slide behind again. So the capability is currently kind of big. I'm working on making it smaller, don't worry. It's got a lower bound, an upper bound, some flags, and a 1 byte word type for every 16 bytes of payload. So the raw pointer can point anywhere in the payload or even out of bounds of the payload. The capability pointer always points at the base of the capability object. And in the common case, like if you call malloc, this whole thing is actually one GC allocation. The payload is just at the end of the capability. But that's not always the case. It's just the common case. So for example, if I call malloc 48, note that unlike something like effective SAN or secured, there's no need to annotate this malloc call with what the type is going to be. You call malloc 48, and what you get is an object that is 0 initialized in the payload, and the word types are all initialized to unset. That's where the monotonicity comes in. Each word type can monotonically transition from unset to either int or pointer, and then monotonically from there to free, but not ever in the other direction. So when I happen to store to the first word with an integer access, that monotonically transitions that first word from unset to int. And then when I do something crazy, note that this is like so crazy that maybe the C spec doesn't even allow it. Who cares about the C spec? Like if you're writing a C compiler, you don't implement the C spec. You implement like the C that real people use. So real people do that. So if you're implementing a C compiler, you have to support it, and I support it. And the way that that works is P plus 4 is at offset 16, so that puts you in that second word. That second word started out as unset, so that store succeeds in transitioning that word type to putter. So that store just works. And then when I free the thing, then all the capabilities monotonically transition to free, and at that point, all accesses to that object will fail. Moreover, once the capability transitions to free, then on the next garbage collection cycle, when the garbage collector finds this pointer, it'll, rather than marking the capability in the payload, it'll just repoint the capability at the global free singleton. So freeing an object causes the next garbage collection cycle to really free it. This is important because if you take a malloc and free system and throw a garbage collector in it, you often will create memory leaks that weren't there before because people just kept around dangling pointers and happened to never dereference them. But in Fil-C, that is not the case. If you enable Fil-C, you're not creating new memory leaks because the freed objects do get freed. It's just that the actual reclamation of memory is deferred until the next garbage collection cycle. So monocaps give me this combination of maximal safety and maximal compatibility. There's no need to annotate or infer the type of malloc calls. You just call malloc however the hell you want. And then the types of that malloced memory are inferred dynamically, and the free itself is deterministic. After you free the object, every subsequent access to the object is guaranteed to fail, no matter what. So some additional monocap features that I won't be able to talk about because they're actually kind of deep. Function pointers, monocaps tell you about function pointers so that you can't get type confusion from indirect function calls. Monocaps handle mmap and munmap, including shared memory uses of mmap, so you can do shared memory IPC memory safely with Fil-C and it just works. They handle DSO handles, so you can do DLOpen and DLSym, so dynamic linking with Fil-C. That's memory safe and it just works. Threads, jump buffers. Fil-C has long jump and set jump, and long jump and set jump are memory safe. And the rules of long jump and set jump are dynamically enforced, so you can't set jump to somewhere you're not supposed to be set jumping to. And signal handling, so signal handlers work. So like you can register a signal handler and long jump out of it, whatever. Like so long as you're doing it the way that the manual tells you you're supposed to, it'll work in Fil-C. So how does the runtime work? I call it the libc sandwich runtime. In general, on any OS that you would port Fil-C to, what you would do, oh my gosh, I'm one slide behind again. Okay, there we go. What you would do is you would run the Fil-C runtime on top of whatever the libc is on your OS, just so that Fil-C's runtime can get syscalls. And then you compile that libc with Fil-C and run it on top of libpslow. So that but also make changes to the libc so that normally libcs make syscalls with like inline assembly or standalone assembly files, but the Fil-C version of the libc makes syscalls by calling into private API exposed by libpslow. And then libpslow filters every syscall for memory safety. So you can't use syscalls to escape memory safety. There is no escape. Fil-C will crash the shit out of your process if you try to escape. And then just compile all the rest of userland with Fil-C on top of that, and you get a memory safe application. All right, so the current implementation I call the musl sando. Musl is freely available libc for Linux, and so I'm running YOLO musl below and user musl above. The YOLO musl is basically unmodified. The user musl is modified just to change how it does the syscalls. Here's an example of like how that ends up working out for a very simple system call. You can see like if you do the right system call in the user musl, it's just going to call an internal API called zsyswrite. That's all it can do. And then zsyswrite is implemented in the libpslow runtime, and it's first going to check pin and track the buffer, check that it's an integer buffer that it can be read from, and that there's size bytes of integers available in it. It pins it so that the garbage collector doesn't do anything funky, and then there's this Fil-C syscall wrapper around the actual syscall that does the thing that accurate GCs do, where it tells the GC, okay, I'm making a syscall now, so I'm at a safe point. And then YOLO musl does the syscall the way that musl usually does, which is with its macro that expands out into a bunch of inline assembly. So that's the basic pattern of how like syscalls look like in Fil-C. Okay. And syscalls are the only case of foreign function invocation between Fil-C and legacy C, and it's that foreign function interface is not exposed to anything other than libc. So there's a ton of complex features that just work. For example, I'm still one slide behind. So for example, C++ exceptions just work because libpslow provides a comprehensive unwinding API. mmap, shared memory, dynamic linking, signal handling, fork. You can fork. You can start multiple threads and then fork. You can cause the GC to run and then fork. All works. So yeah, lots of stuff just works. So how do I do this inside of LLVM? This insight that I'm going to tell you about is like one of the things that got me started on the project, and it's just a little bit of inside baseball about how LLVM work. So this is the LLVM pipeline in like very coarse grain box diagram. You got Clang. Clang does code gen, and then you get the whole sausage factory that is LLVM. Here's the insight. So in LLVM, there's the only pointer type is just pointer. You know that it's a pointer and you know nothing else. You don't know what it points to. In Clang, you have like a whole AST that describes C types, which don't really mean anything because in C you can cast anything to anything. The way Clang code gen works is it's remarkably well behaved with respect to pointers. Namely, what I call the pointer versus integer intent is preserved. That is, if in your C program you had a variable or a field or something whose type was either pointer or reference or anything you would think of as a pointer as a C programmer, then that field all loads and stores to that field or that local variable is going to be transformed into LLVMIR that says PTR for the type of that thing. So when you're looking at LLVMIR, you have now, LLVM can bitcast pointers to integers. So as soon as you actually run the LLVM optimizer, the intent is no longer going to be preserved. But at that precise moment when you came out of Clang code gen, the integer to pointer intent is preserved. So you have something that's almost like an emergent type-safe language where the only type is pointer versus everything else. And this is generally true for a lot of things. There's a couple of places where it's not true. It's not true in the CG atomic portion of CodeGen. There it does bitcasts between pointers and integers in weird ways. And some of the implementations of sophisticated C++ language features also do weird bitcasts. But those are all easy to fix. There's no like profound reason why it does that. So here's how I implemented version 0 of the Fil-C compiler. I add the fil-pislinator pass, and that pass enforces GIMSO not on C, but on LLVMIR itself. So no matter what LLVMIR you give it, the output will be a program that enforces that pointer to integer intent of that IR. So every pointer load does checks that it's loading from a memory address that is allowed to be a pointer. Every pointer store does the, and then every integer load and store does the corresponding checks. All allocations are diverted to my runtime, et cetera, et cetera. So this is, you could give the Pizzolinator pass any LLVMIR you like, and you'll either crash the pass, or you'll get a program that crashes with a Fil-C panic. You might violate the rules, right? Like if you do bit casts that are bad, or it'll run and it'll run memory safely. And so then version 1 was I just started adding more optimizations to run before the Pizzolinator pass. So I'm running most of the core LLVM meat grinder of optimizations. So it's the inlining fixed point that does SROA, which is like escape analysis for locals, GVN, which is load elimination, and other kinds of CSC, inst combine, a bunch of other stuff. And then to make it even better, I then added an abstract interpreter to the Pizzolinator pass so that instead of emitting checks blindly, I'm emitting a minimal set of checks for some definition of minimal. It's not like the best abstract interpreter you could possibly make, but it's a decent abstract interpreter. So results so far. I can compile bzip2, zlib, mg, both of the versions of PCRE, as if you're familiar with the Perl compatible regular expression library, there's like 2 of them. And ncurses, those compile with no changes and just work. And then there's a bunch of stuff that work with small changes, including CPython, SQLite, Lua, OpenSSH, so I can run the OpenSSH server and client, OpenSSL, links, so I've got a memory safe web browser, libc++ and libc++ ABI, and anyway, a bunch of stuff. In the best case, it's like 1.5x slower than normal C right now, and in the bad cases, it's like 5x slower. But it's getting faster and faster. I'm working on another speed up right now. So the 5x number will keep shrinking. All right, that's my talk. Thank you.
Hey, Phil.
Hey.
Good to see you. Great work. I've long said that C and C++ are secretly safe languages. It's just the implementation. So I'm really glad to see this work. I guess I have some like high-level questions and low-level questions. I'll just be brief. High level, like how far do you want to take this? What's your goal? A medium level one is what do you think the major sources of slowdown are? And which ones are going to be tractable to reduce and which ones not so much. And then low level, I couldn't help but see that you have this word-based capability boundary. What happens if you do crazy things at a subword level, or is that just in like a thing? Like if you were at a subword level, yeah.
Okay. So the first one, remind me. High level goal. I want to troll a compiler team into making something better than this. So that would be the best outcome. Or to get somebody to actually use this in a serious enough setting that it just kind of takes on a life of its own. Either one of those. Mid-level, remind me. Performance. So the number one reason for the 5x is that the monotonic capabilities really are memory safe, are really thread safe. So when you do the first store to a word, it's a compare and swap to compare and swap that word type. And my next change is about just getting rid of that, changing the capability model a little bit so that I don't have to do that. And if you do subword, then like you still check the whatever 16-byte word you're in. The part of what the abstract interpreter does is it like looks at all of the accesses to a range of memory and finds like the minimal set of instructions to check. That gets hairy, but that's how it works right now.
So would Cherry hardware alleviate some of that performance?
Cherry
issue?
hardware would make it so I can't run CPython.
And why is that?
They can't run CPython because there are nasty things in the CPython bytecode where the way CPython normally does it is it stores 64-bit pointers. They have to be 64-bit, like it's very hard-coded, on 2-byte alignment within the bytecode stream. So that completely breaks Cherry. And because I have a garbage collector, there's like having a GC means that you can do these localized hacks where like, oh, I have a lookup table here. I just allocate it. Who cares when I free it? So I was able to very straightforwardly like make that code just work so that it's storing a 64-bit index that then happens to get looked up in a table. But the Cherry people never were able to get that to work. So on Cherry, the best you could do is MicroPython. And I suspect there are going to be other cases of this. Basically, having a GC means if you find yourself in a region of someone's code where like the capability model is too strict, it's too much of a straitjacket, you have this like off-ramp where you can be like, well, but I have a GC, so I can just like malloc myself something and not worry about it. So I wouldn't want to run on Cherry because like it would make me less able to run stuff. Also, silicon economics are all about volume. So like Cherry wouldn't be a speed up for me right now. I guarantee you any hardware you can get that runs Cherry is going to run XZ slower than I just ran it. So like the correct way to get better performance is to keep running this on stock hardware, and then if it gets big enough, then the CPU designers are going to use traces of Fil-C's checks in their optimizations, and then it's going to get faster.
You didn't say anything about what doesn't work. So, for example, can you XOR 2 pointers together and expect things to come out right?
I mean, first of all, in C, if you tried to XOR 2 pointers, that is one case where the compiler will actually give you a compiler.
Oh, I mean, cast them to integer and XOR.
And yes, you can do that.
And it works.
The main thing that doesn't work is pointer-integer unions where you change your mind about whether you're using pointer or integer. And I'm actually, the change that I'm working on right now that's also going to be a speed up also puts me in a mode where I can allow unions to flip-flop. So I'm like, when I become aware of something that doesn't work, I fix it. But the biggest practical thing that sucks is if not having inline assembly means that like any sufficiently large C program doesn't compile immediately out of the box because you have to, at a minimum, just tell it not to use the inline assembly.
Hi, we're the CPython devs that introduced those inline bytecode caches, so sorry about that.
Oh, no problem.
But you mentioned that it needed some changes. Are those compatibility things like support for fat pointers mostly, or is it working around bugs in the implementation, or are they true memory unsafeties that need to be upstreamed?
There was one memory safety bug that I found, and I filed a bug, and y'all fixed it the same day. It was super awesome.
Awesome, thank you.
The other stuff is like, for example, in the GC implementation, the header in the way CPython is written uses uint ptrt. I just had to change that to void star to make that work. So like you could imagine upstreaming that to CPython and it wouldn't make any difference whether it's void pointer or uint ptrt for people compiling with normal C, but you can't use uint ptrt because as soon as you cast a pointer through uint ptrt, once you cast it back to a pointer, you get a pointer with a null capability and you can't access it. So if you want to actually play games where you have a pointer, even pointer like that uint ptrt has like high bits, low bits, whatever. You can do that with a void star. It just has to stay a void star if you ever want to go and dereference it. So that's like the biggest change is, that's why it's like a 50 kilobyte patch, because once you change the types of those fields from uint ptrt to void star, there's like multiple files where you have to kind of, you know, adapt to that.
Hey, thanks. Two small questions, I guess. The first one is, so does it have like capability with LLDB for like debugging capabilities so far? Or, okay, cool.
No.
That kind of makes the other one moot, then never mind. Thank you.
I want to add that. It's just that like, I completely corrupt the dwarf in my transformation right now. I'm not preserving it at all.
Hey, some nuts and bolts questions about the GC. Do I understand correctly, since there's no stop the world, it's a fully concurrent, you don't have the problem of figuring out where to put save points because you just don't need them in like a multi-threaded program?
No, it's like it uses the soft handshakes that you would find in a DLG collector. So there are pull checks, as I call them, sprinkled by the compiler. Also on the slide where I had right there, Fil-C syscall actually calls Fil-C exit before the syscall and Fil-C enter after it to tell the GC, hey, you don't have to wait for a pull check from this thread right now. So it does all the things that you would expect like a Java VM's GC to do in order to interact with the mutator. But there's no global stop the world where you like stop all the threads at once and then do some stuff. It's the GC asks, hey, all threads, please check in with me, and then when they all do, then the GC makes progress.
Thanks. Second unrelated question. So you said you'd rely on this invariant that happens to hold in Clang CodeGen. Is that an emergent invariant? Like, do the Clang team care about that in the long term, or what?
Thank goodness for GPUs, man. It's an invariant that they, I think, had to enforce because the pointer integer distinction is particularly meaningful when you're compiling things like OpenCL. So I think that's why they're careful about it.
Cool. Thanks.
But if I was writing a C compiler today, and I wasn't in the business of memory safety, then my intermediate IR wouldn't even have a pointer type. I would just have integer types, and my load instruction would take an integer, which is, by the way, what I did in the B3 backend in JavaScript core. It just has integers. So if I was in a world where I had to convert my own C compiler to Fil-C, then I'd be completely screwed because I wouldn't even have a pointer type. So there's the danger that like in there's some future version of LLVM that just gets rid of the pointer type. And then I'd be sad and the GPU people would be sad.
So I'm sure you're aware that the Rust people are super excited about the documents coming out of the federal government regarding safety.
Yeah.
And they're convinced that they're going to be the torchbearers, right? And will strip C and C++. So I guess I have two questions about this. I mean, once you make CPython actually memory safe, then Python is safe modulo all its packages that aren't safe. But in principle, you could recompile them.
You have to in Fil-C.
Yeah, right. Which is a challenge, I expect, but not such a challenge for things like NumPy and stuff. Like, the only question is if they call out to BLAS, that's going to be a deal breaker. So performance is going to be a killer in that space. I feel like there's things like OpenSSH are the sweet spot for this kind of work, like very clearly security sensitive, internet facing things. So I mean, I would propose that rather than just hoping that some compiler team picks this stuff up and runs with it and makes things even faster, that you make it available as a tool, if you can, that people can use to build this software when they just want a hardened OpenSSH.
It's available today. Like you can go on GitHub and check it out and build it. If you're on Linux x86-64, it just works. So I actually think that I mean, part of the reason why I'm doing this is I want to obviate the need for Rust. And so like I'm not there yet performance-wise, but I will get there. And if you have suggestions for how to con people into using it, I'm all ears. I mean, this is a brand new project, right? I started in November of last year, so I have had only a small number of opportunities to even. This is the first time I'm talking about it publicly, for example, other than YouTube, and trolling people on Twitter.
I think since it's been a bit over time, we can go ahead and go to lunch and then take the rest of the questions offline. So let's thank our speaker again.
Thanks, y'all.
Test 1, 2, 3. That's it. And the one for the questions.
Test, test, test. Yeah, I think it's good.
All right. Hello, everybody. It's my pleasure to start the next REBASE session. Right now, we will have 3 talks. We start with Eddie. So without any further ado, the floor is yours.
Thank you. Again, my name is Eddie Aftendillian. I'm a principal researcher in GitHub Next. I was a member of the original GitHub Co-pilot team, and I led some of our more recent projects, specifically Copilot for Docs and Copilot Workspace. And today I'll be sharing some lessons that we've learned from building these GitHub Copilots. Can people hear me? Can you hear me in the back of the room? No. Okay. Hello, can you hear me now? No? Hello? Hello, hello? Do I have to get this close? Still can't hear? Hello, can you hear me? Okay, that's better. How about from here? Or do I need to stand like right at the mic? Maybe I'll just hold it. Okay, is this good? All right. Okay, so I'll be sharing some lessons that we've learned for building GitHub Copilots. So in case you haven't heard, AI developer tools are changing the way that we write software. And GitHub Copilot was one of the first such tools. It launched as a technical preview, essentially a closed beta, in June 2021. Today it has 1.8 million paying users, and 50% of those users' code is written by Copilot. For context, estimates are that there are maybe 20 to 30 million software developers total in the world. This is a pretty good chunk of like all software developers in the world. And other companies such as Google report similar proportions of AI-generated code for their comparable AI code completion tools. And this is only going to increase as the next generation of tools comes online. These are tools that approach the problem at a higher level. For example, completing an entire development task as opposed to completing a line of code or a function. These are tools like Copilot Workspace, Devin, Cursor, and so on. In GitHub Next, we build AI developer tools. We're a research or advanced R&D team within GitHub. We created the original GitHub Copilot in collaboration with OpenAI. We also created something that was branded as Copilot X, which included Copilot for Docs and a few other projects. And most recently, Copilot Workspace. And along the way, we've also tried a bunch of stuff that didn't succeed. And so we've learned a lot from working on AI developer tools for the last 4 years. And today I want to share some of those lessons with you so that everyone can build great AI developer tools. I'm here representing the work of an amazing team. Currently we have 19 people. We have a couple of new people who are not represented on the slide. We have a mix of backgrounds and skill sets. We have some front-end developers, we have back-end developers, we have ML researchers, we have programming languages researchers, we have user researchers. And it takes this diverse mix of skill sets to build successful AI developer tools. And so I'm going to share these lessons that we've learned over the last 4 years, and I have divided them into 2 broad groups. The first are organizational lessons, and this next are technical lessons. And I'll conclude with the 3 most important lessons that I want you to take away from this talk. So the first category are organizational lessons. Setting up a team to do this kind of innovation work is actually very difficult, but having the right organizational setup is critical to making it work. The first organizational lesson I want to share is to think big. Being a research team within a big company is a precarious job. You're different from all the other teams. You're not delivering immediate value to an existing product, like a product or engineering team. And what you work on is risky, and much of what you try is going to fail. And so for this kind of team to succeed, you need to bet on things that have the potential to deliver asymmetric value far beyond the effort required. Now, you might ask, is it realistic for a small team to think big? It's more realistic than you might think. And here I wanted to share the example of Original Copilot. When Original Copilot was introduced in June 2021, there were fewer than 10 people on the team. One of the great things about software is that a small team of great people can build something with huge impact. And this is what I meant by asymmetric value on the previous slide. In addition, building an ambitious new thing can actually be easier to do organizationally than shipping an incremental improvement to an existing product. If you're trying to get a new feature into an existing product, there's a product team you have to interface with. You have to convince them that they want the thing that you're building. And if you build it and try to hand it over to them, they might balk because you're treading on their turf. You'll run into all the standard problems of tech transfer that industry research teams struggle with. But if you're building something totally new, then there's no team whose turf you're treading on, and you don't have to get their buy-in. We call this non-adjacency, and it's a core principle in Next. Does our idea represent an incremental enhancement that GitHub engineering would naturally do at some point? Or is it a fundamental rethinking of a problem that we're uniquely positioned to solve? We want our projects to fall into the second category. Back when we created Co-pilot, GitHub wasn't building IDE extensions and wasn't working on code completion. And this made it easier to make the case to launch this project. The next lesson is to deliver tangible results frequently. If you're thinking big, it can be tempting to talk about multi-year time horizons. It's okay to have a long-term vision and an overarching plan, but you need to drop off useful things regularly, or it's going to look like you're doing nothing. And the example I wanted to share here was some of the work we did on neural retrieval. In late 2022, we built a homegrown vector database to experiment with. Retrieval was a hot topic in the ML literature, and we wanted to see what it might be good for. We first used it to explore natural language code search with a deliverable of a live demo at the GitHub Universe conference in October 2022. While it demoed well, the quality of the search results wasn't good enough for a real product, so we moved on to another application. Next, we used it to experiment with customizing Co-pilot for private codebases. Because Co-pilot uses standard models that were trained on public code, they're not aware of a company's private code, internal APIs, custom programming languages, and so on. And so we were looking for a solution to improve quality on these private codebases. One way to do this is to index the private codebase and store snippets in a vector database, and then as the user is typing, you query the database for similar code and inject it into the prompt. So we implemented this, and we ran an offline evaluation and got a very positive result. But when we ran an online A/B test in Co-pilot, we didn't see any improvement in our key metrics. And we had another application for retrieval, so we handed this result in our code to the Co-pilot team, and we moved on. By this time, ChatGPT had been released, and everyone was excited for chat. We realized that you could use retrieved snippets to ground an LLM chatbot in high-quality official documentation. We also realized that you could retrieve from private documentation as well as code to customize the chatbot for a specific company. So we refocused on retrieval-augmented chat, which turned into Co-pilot for Docs, which launched as a technical preview in March 2023. With the retrieval work, we were able to deliver 3 useful things, each taking a few months, along the theme of investigating neural retrieval. Next lesson is to create urgency via deadlines. Setting deadlines focuses the team, it forces you to make hard decisions, and great teams will rise to the challenge. These have to be real deadlines with an external commitment. People are smart and will see through fake deadlines. The academic equivalent here is committing to a paper deadline, and I'm sure you've all seen how much progress you can make in the week before a paper deadline. You do have to be protective of team health. You can't always be crunching. You need to balance these with less intense times when the team has room to explore new ideas. And the example here I wanted to share is Co-pilot for Docs again. So we had this vector database lying around, and we were able to build a demo very quickly once we got this idea. So we built that demo. This demo got sort of shown around to executives, and we were immediately asked, why haven't you shipped this yet? Could you have it ready in 8 weeks? So I went back to the team, we discussed it, and we decided to go for it. And once we made that decision, it became a sprint. We couldn't argue about stuff for even a couple days. We had to make quick decisions and push forward. It was fun to rally towards something big. And even though it was intense, the people who worked on Copilot for Docs will tell you that it's the most fun they've had in Next. Next lesson is to be disciplined in project selection and continuation. Next aims for an 80% failure rate, because if we're succeeding too frequently, we're not being ambitious enough. This means that most projects are going to have to end before they reach their goals. It's tempting to let stagnating projects continue in the hope that they're going to unstick themselves or to avoid conflict. And in fact, many of these projects are not stagnating. They're progressing, but not fast enough or easily enough. Maybe they've hit a roadblock that is solvable with enough effort, but there's an opportunity cost to that. What are you not working on because you're working on this? And this opportunity cost is especially high in the LLM era, when models are improving exponentially. Also, the longer a project goes on, the more painful it is to stop it. If you've been working on something for a year, it's going to hurt much more if you have to stop that project than if you've only worked on it for a few months. Here's an example of a project that didn't continue, SPLASH'. SPLASH' was very ambitious. It explored whether you could write a natural language specification of a whole application and have an LLM compile it to code. And the core idea was that the natural language should be the source of truth, not the code. As we worked on this, we ran into some hard problems. First, it's very difficult to iterate when natural language is the source of truth. One of the principles of SPLASH' was that you shouldn't need anything beyond the natural language spec to compile the same code every time. But in practice, it's really hard to specify an entire application in that level of detail, not to mention dealing with LLM non-determinism. You might get something close to what you want on the first try, but then you can't adjust just one part of the application via this interaction. And the second hard problem was that it's just hard to generate a full, real application from scratch. It's hard to specify how you want it to work, it's hard to break it down into components, and so on. As this project grappled with these hard problems, other projects sprung up that needed help. So reluctantly, we paused SPLASH'. And SPLASH' didn't fail. Its core ideas influenced the rest of Next and led to the creation of Copilot Workspace, which I'll discuss in just a minute. Next lesson is to beware of long-term project ownership. As a research team, your job is to invent new things. Time that you spend maintaining things that you've already built is time that you're not spending building new things. My teammate Idan Gazit has a saying, "You can't go exploring if you're carrying baggage." If you've ever been in the situation of trying to maintain an existing project while building a new thing, you know how hard this is. It's very difficult to justify spending time on something new and speculative when you have real users who are running into bugs in your existing thing, or who have feature requests that you know will improve their experience. But as a research team, you have to spend time on the new stuff because that's your job. And so it's very important that you not hang on to projects for too long. You need to get these projects to a point where they can stand on their own and then hand them off to a product team to own long term. With original Copilot, this was a long process. Those of us who had created Copilot in Next went on loan into GitHub engineering to seed and grow the new Copilot team. We helped to get Copilot to general availability. We hired people who could take over our work, and we worked on knowledge transfer for almost a year to help build a healthy team that could own Copilot long term. Then we came back to Next and started working on new projects like Copilot Workspace. Next, I want to share some of the technical lessons that we've learned. And the first lesson is that UX is critical, not just in AI developer tools, but in any developer tool. In the programming languages and software engineering communities, we have a long history of building really cool, innovative, useful tools that no one uses. Some examples, refactoring tools, right? So people do use refactoring tools, but they underuse them. There are a lot of like really useful refactoring features that people never use. And there's been a line of research in the software engineering community investigating, why this is. Why don't people use refactoring tools? Static analysis tools are another one, right? So we talk a lot about static analysis tools here, but in practice, most engineers are really only interacting with, maybe a linter on a day-to-day basis, but not real heavyweight static analysis. Program verification or formal verification tools. I don't think I have to explain to this crowd how hard it is to get uptake of these tools. Even debugging tools are not actually very widely used. Even basic debugging tools like your debugger. I don't have hard data on this, but I would estimate that the majority of developers are just doing printf debugging. They're not using a debugger. And this list goes on and on. And I think this is because we haven't found the right UX to make these usable by real developers. And usually, the people building the tools don't have UI expertise to find this right UX. But getting the UX right can be the difference between success and failure. And here I wanted to show the evolution of the Copilot Workspace UI as it evolved from a prototype to a product. So Copilot Workspace aims to help a developer solve an entire development task, such as a feature request or a bug report. It takes in this development task as input. It finds the right places in a repo to address it, and then it modifies the code to satisfy the requirement. This is what the first prototype of Copilot Workspace looked like. It was an experiment by one of our team members, Don Syme. He had been inspired by SpecLang, but where SpecLang wanted the natural language to be the source of truth, Don wanted to explore keeping code as the source of truth, but enabling the user to modify it by editing a generated natural language specification. So he called it extract, edit, apply. The user would first extract a specification of the code in the repo with respect to some topic. Here it's called the pivot. Then edit that specification, and then apply that edit to the code to update it in the way desired by the user. Now, Don is brilliant, but he's not a front-end developer. And so you can see that this is rough, but it gets the idea across. And we've kept the core flow of extracting a specification and now a plan, and letting the user edit those and then apply or implement the changes in the code. This is the first publicly shown version of Copilot Workspace. It was demoed at GitHub Universe in October 2023, about a year ago. At this point, we had brought on our first front-end developer, Cole Bemis, and he totally revamped Copilot Workspace, and it looked amazing. Cole had previously worked on GitHub's design system, Primer, and you can see his fingerprints on this. It's now consistent with GitHub's design language, and it looks like a real product. After Universe, we brought on a second front-end developer, Turkel Gervig, and he revised the left-hand side with a timeline view. This makes it clear how you are supposed to progress through the flow. You start with the issue, you proceed to the specification, you generate a plan, and then you implement the code changes. This version lasted the longest, from around March 2024 until very recently. This is the latest UI revamp, which just became the default about a week ago. We heard feedback from our users that they wanted help from Copilot Workspace before starting to implement. Often you might have an issue where you don't actually know how to solve it, and users want to brainstorm possible approaches with the AI in the context of that issue in that repo. And so this version focuses on the brainstorming side of Copilot Workspace. You'll note that it removes the spec and plan. This is a big change and one that we experimented with for quite some time. While we're continuing to refine it, early feedback from users is very positive. We spent a lot of time and effort on the UX of Copilot Workspace, and we believe that having a well-designed and polished UX is critical to making it something our users love to use. Next lesson is to build a prototype ASAP. As researchers, our instinct is to run benchmarks and quantify things, but feel is actually very important when building developer tools. And to get a feel for a tool, you have to build a prototype and use it. Also, a prototype is far more convincing to decision makers than benchmarks. And as an example, I wanted to share a project I worked on at a previous job called FixBot. I started FixBot with the aim of automatically repairing code that doesn't compile using a model trained on source code edits. Oops. This was before LLMs, and so we had to train a model from scratch to do this. We started by collecting a giant data set and then training that model, then computing the fraction of failed builds that we could fix. We could map that to developer time and show huge potential productivity improvements. But my management wasn't convinced, and it took us years to do all this work. If I could go back, I would do the least amount of work necessary to build a prototype that we could show to the decision makers, let them use, and so on. A usable prototype is much more convincing than charts and graphs, even at a data-driven company. In addition, having a usable prototype lets you test your assumptions. In Fixbot, we had some assumptions that made the project significantly more complex. For example, we believed that we couldn't show fixes that wouldn't compile to developers, and so we did a lot of work to implement what we called speculative builds. But if we had had a prototype, we could have just tried using it before we built that feature, and maybe it wouldn't have been necessary. Or maybe we could find a UI that lowers the cost of these incorrect suggestions. The next lesson is to do the simplest thing first. As researchers, one of the mistakes we make is valuing difficulty or novelty, when really we should celebrate simple solutions to hard problems. This is doubly true in the LLM era. If you can solve a problem purely through prompting an off-the-shelf model, you should do that. You should only move to more complex solutions if you absolutely have to. And it's surprising how many problems you can solve with simple approaches. And for example, I wanted to share a Copilot feature that we built called neighboring tabs. In the early Copilot days, we would send context from only the current file to the model. But it was clear that context from other files could be useful as well. So we implemented the simplest possible form of this, where we looked at other files that were open in the editor, did a very basic textual similarity match, and then inlined the relevant code into the prompt. What we did not do was spend months discussing this, over-designing it, training embedding models, setting up a client-side vector database, and so on. When we ran the A/B test, the result was striking. The improvement was comparable to the improvement we got from switching to a newer generation model. It was the single largest improvement we ever got through prompting. And while we had a bunch of work planned to make this feature better, we never did it because the basic implementation worked well enough and there were other lower hanging fruit to pick. Next lesson is to build an evaluation suite. So I mentioned earlier that feel is important, but quality is also important. In order to make decisions about things like choice of which model to use, your prompting strategies, and so on, you need some way to measure quality. This doesn't have to be perfect, but it does need to give you, enough signal for you to make decisions. The example here I wanted to share is the Copilot offline evaluation harness that we built. So this was for classic Copilot code completion scenarios. And the way it worked was that we took real open source repos. We would clone these repos. We would install the dependencies and get them set up to the point that we could run their tests. We would run those tests with coverage enabled, and then we would look at the functions under test. We would select functions under test that had high coverage, and then we would treat those as targets for synthesis. We would blank out the function bodies of those functions, and then we would query the model for a replacement function body, and then we would rerun the test. And if the tests pass, then that would be considered a success, and if they didn't pass, that was a fail. Now, this offline evaluation harness was limited. It only supported 2 programming languages, because we did have to figure out how to set up the dependencies and run tests in the language, so there's per language work we had to do. It only supported Python and JavaScript, and it also only tested full function synthesis. So, actual Copilot has multiple modes. It can suggest sometimes only a single line, sometimes it will suggest to the end of the current block that you're typing, and sometimes it'll suggest a full function. But our offline evaluation suite only tested full function synthesis. So it wasn't perfect, but it gave us enough signal to make decisions, and it was especially important before we had real users where we could do A/B tests, which are kind of the gold standard here. Next lesson is to don't over-index on cost. we're in an era of exponential improvements in LLMs. This means that costs have been quickly going down and will continue to do so. And so we shouldn't prematurely declare projects too expensive. Instead, we should focus on delivering the most value to the user and assuming that exponentially decreasing costs will make it financially viable. When we built Copilot, there were existing competitors, but they were all using small local models, presumably for cost reasons. With Copilot, we were aiming for much higher quality, which required a large cloud-hosted model. It would have been easy to just decide that this was financially infeasible and kill the project, but instead we focused on building the best tool we could and getting users to love it. And it succeeded. And over time, the models we use to power Copilot have gotten smaller and faster while quality has improved. We saw a similar thing with Copilot Workspace. When we started the project, we were using the preview version of GPT-4, which was terribly slow and expensive. But then GPT-4 Turbo came along, which was much faster and cheaper. And now we have GPT-4o, which is quite fast and quite cheap by comparison. Okay, lesson number 6 is keep an eye on the literature. And here I kind of mean the ML literature. The ML literature moves super fast, and it can be really hard to keep up with it. The models are improving exponentially. But if you pay some attention to the literature and maybe social media to see what people are talking about, it can be useful to see what new technologies people are excited about. And sometimes you want to make a bet about how you think things are going to evolve and start moving in that direction before everyone else. And the example here, again, is neural retrieval. So back in 2022, we were reading papers about retrieval-enhanced models, and it seemed like this could be an interesting solution to the problem of adding additional information to an LLM. So we built a simple vector database to experiment with, and that turned out to be the foundation of Copilot for Docs, which we were able to build super quickly because we already had that core technology in place. And then the next lesson is to dog food intensively. Dog fooding refers to the practice of using the things you're building. It comes from the phrase, eat your own dog food. And surprisingly, a lot of people don't do this, or they disregard the feedback when it's inconvenient for them. In Next, we dog food intensively, and we take the feedback seriously. It often results in substantial changes to the things we're building. And here, I wanted to show some examples from something that we call Copilot NES, or Next Edit Suggestions. Copilot NES is a current project that aims to take AI code completion to the next level. Original Copilot suggests code where the user is typing and only takes into account the current state of the file. Copilot NES takes into account the sequence of edits the user has made and predicts the likely next one. This edit doesn't have to be at the cursor. It can be somewhere else in the current file. For example, suppose I add a new parameter to a function declaration. Most likely, my next edits are going to be editing the call sites to pass that new argument. NES will suggest those edits away from the cursor. At the beginning of the project, we had a strong belief about how we should present those diffs, with strike-through text and a replacement in this light-colored text, which we called ghost text, like original Copilot does. When we started dogfooding it, however, we found that when the ghost text appeared, it would cause text later in the file to shift around in a very distracting way. Our dog fooders reported that it was very irritating to have their screen constantly shifting around like that. So we reluctantly implemented this side-by-side diff view, and it was immediately obvious that this UI was better. The team member who had been most opposed to it quickly admitted he had been wrong. And now it's time to shift gears and wrap up. If you take away only 3 lessons from this talk, I want them to be the following. First, think big. Don't settle for incremental improvements. LLMs are able to solve problems that were previously impossible, and our job is to figure out how to make these capabilities really useful to developers. Second, UX is critical. Building a great developer tool is not just about the core technology, but also about how easy and fun it is to use. Don't overlook this critical aspect of building AI developer tools. And third, dog food intensively. You really need to use the things you're building, and you really need to listen to the feedback and address it. Thank you for coming to my talk, and I'm happy to take questions.
thank you. Okay. Thank you a lot for the talk. It was very interesting. I wanted to ask you, how important do you think it is? It would be to keep a business motivation in mind, like an application for business. Like, is it more important to be able to dog food something and do something that the researcher is excited about, or do you think that it's not worth doing it if you don't see a business application?
Yeah, so this is a good question. I actually think that over-indexing on business, like a business application, is a mistake. I think one of the fun parts about working on developer tools is that, like, as developers ourselves, we're our own users, right? So in a lot of other software domains, you're building software for users who are not you. Like, they have different characteristics. What resonates with you may not resonate with them. But in this area of developer tools, like, we're all developers, we all use developer tools. And I think usually our intuitions about what a useful developer tool is are actually correct. And so sort of over-optimizing for a business case might prevent you from building a more generally useful developer tool that can be broadly used. And I think, you know, in the one project that I look up to from this perspective is VS Code, right? So VS Code, you know, it's a Microsoft product. It's kind of cannibalizing from Visual Studio. But on the other hand, like, that team has made like really good decisions about making it a tool that is generally useful for all developers and not over-indexing on the business case for it. And I think they've had huge success because of that. So I guess my position here is that you should build a tool that is most useful to developers and that they truly love, and the business case will work itself out.
Thank you. I really enjoyed the talk. I had a quick question. I think you mentioned before about you can't like stew on an idea for so long, and then and velocity is important. Please correct me if I'm wrong, but I thought at least like I think GitHub is not like startup level lean, and so I'm having a bit of a difficult time like associating the word velocity and a big company called GitHub together. How do you manage to keep velocity in your team?
Yeah, so this is an important point about how our team specifically, GitHub Next, is set up, as opposed to being the rest of GitHub, which has to operate at a sort of a more measured pace because you have enterprise customers who've signed agreements, and if you change the UI, like, people are going to be upset. So in GitHub Next, we're a small team. We're like 20 people. We have a lot of autonomy to sort of build things as we see fit. And so this means that, you know, we're able to move quickly in a way that like production teams cannot. And you know, we own decisions ourselves, right? So like when we're building Copilot, we don't have to negotiate with you know, someone in some other team to do something. We can just make a decision within our team and move on. And that actually is what enables a lot of this velocity, is this sort of you know, the combination of having people who are empowered to make the decision and make good decisions, and also, you know, having the autonomy to be able to make that decision without, you know, showing 10 decks to executives and so on.
Thank you.
All right, so let's thank the speaker again.
Do you want to present in presenter mode, or you're okay with the slideshow?
Whatever is easiest for you. I don't mind either way. right, well, thank you, everyone. I'm trying to keep it a little bit light and fun today. So yeah, I want to talk a little bit about going from AI software engineers, or maybe from software engineers in general, to AI knowledge workers. I've been in this area since 2017, when I switched from programming languages to using AI to increase developer productivity. At Meta, we had quite a big group of about 100 people where we were building tools to increase developer productivity, system efficiency. And at that time, we were trying to, we thought that code has special structure, it is tree-shaped or maybe graph-shaped, and we need to build custom models to kind of capture the semantics of code. And so we had as I said, 100 people with PhDs in machine learning to do this stuff. We wrote a paper about it, got a best paper award, and then ChatGPT came out, and then I realized these general purpose models kind of beat all the special purpose models that we have. My group was eliminated for a good reason, because it all crap, all these 5 years of work in vain. So that's where we are. But then I really realized that targeting traditional developers is the wrong thing to do. And why is that? So let's take a step back and think, what is the essence of computer science, or maybe what are we doing, right? What is our role in life? And what is what is the ultimate goal of programming? And I think whatever it is, it all boils down to free humans from mundane, repetitive tasks. And if you look at here on the left, this is what we as academics and computer scientists like to do. It's a little bit like navel gazing. We're building tools for each other. Oh, we have machine code. Let's build an assembler to make that easier. Let's build a compiler, and it's all kind of just reinforcing with ourselves. But ultimately, of course, what we want is some business user using Concur, and maybe you are that business user when you kind of come home at the end of this conference to kind of submit their expense report. So things like Concur are the ultimate tools that we as computer science are aiming to build. But of course, everyone that has ever used Concur will know that this is a piece of shit. But I don't know, 50, 70 years of computer science have yielded something as shit as Concur, right? So clearly we have failed. We got we got an F, not even something for effort. We completely failed as a group. So, and the sad thing is that people pointed this out years ago. In the Humble Programmer, 1972, Dijkstra mentioned this. But even in 1968, there was the famous conference where the software crisis was invented, pointed out. And it just really saddens me that we've been talking and writing papers and doing everything for so long, for decades, and still we are not able to write useful software for the end user. Now let's take another step back and look at something that has been successful, and namely that is hardware. If you look at hardware in those decades, thanks to Moore's law, hardware has gotten bigger, more transistors, the hardware has gotten faster. And now that faster hardware has enabled us to write more powerful software. That more powerful software enables to build faster hardware. And this is I think, a virtuous cycle that has driven the industry forward. However, on the software side, the things don't scale. That's where we have Weird's law. It's like, the faster the hardware becomes, the more bloated software becomes. So while this loop it's a miracle that this loop is still kind of like going on, because we're fucking it up on our side. And so what do we do? Well, I think what we're trying to do is we're trying to fix it by introducing process. We're doing like crazy things like Agile, Scrum, and there's whole conferences about it, like, about software engineering and processes, and it's not working. The problem is transistors scale, but humans do not. I think there's a lot of professors here, and I don't know how many PhD students you have, graduate students you have, like maybe 5, 10. But if I say, like, let's double that every year, you'll say, Eric, you're crazy. That's impossible. All right? If you can work in industry and you say, let's increase our teams, let's double it every 18 months, you say, fuck, that's crazy. That's impossible. All right? But on the hardware side, that works, right? We can just keep on pumping out more transistors, and the hardware keeps getting faster. So the real problem is humans. Humans don't scale. Humans are the problem. And what we need is some kind of Moore's law, but for software. And I think the only way, really the only way we can get there is by getting all the humans out of the loop. That's the only way we can make software scale. That's the only way we can ever hope to get something better than Concur. So that's like after my team was dissolved, that's what I concluded. We have to eliminate developers from the loop. And I must say, I'm super sad when I see companies, like startups that work on AI suites, getting so much funding, because that's just throwing money into the garbage and setting it on fire. It's like building tools for blacksmiths. It's it's just throwing money down the drain. What we need to do is we need to say, can we build software without developers? That is the only way we can create a Moore's law for software. All right, so how do we do that? Well, people have tried with low code, no code. And I don't know if there's anybody here that has ever tried low code, no code. I really don't understand how anybody can write applications with that kind of crap. It's like you got you drag and drop stuff together, and then you have to click, and then you end up in some weird JSON thing that has some weird internal programming language that is completely ill-defined, all composed out of strings. And if something goes wrong, you get stuck. The only thing you can do is throw the whole thing away, start from scratch. What's even worse is that I'm not a big fan of version control and things, but they kind of are useful. But these tools cannot leverage any of the tooling that we have built that might be useful, right? It's a completely separate world. And I'm really, honestly, just completely baffled that anybody can really write things with these low-code, no-code tools, especially people that are not developers. But maybe I'm just a really bad developer. So yeah, these low-code, no-code things, they're really low-level imperative code in disguise. They're not defined in terms of the domain abstractions of the users. Typically, the kind of primitives that you have are just call some REST API with some boxes and arrows. They're not leveraging any tools. You cannot debug, you cannot put breakpoints. And I mentioned this already, but the programming languages that are below them are the weirdest I've ever seen. This is like Clown Town, Amateur Hour, and maybe I think the people that wrote this don't even realize that they're creating a programming language. I think there's way too many product managers and crap people out there that have no clue what they're doing, that are involved in building these products for normal people. So these guys should also kind of get away, right? So no developers, no product managers, free the end user. Free the end user using AI. Now, what we have been trying to do as our field is like, oh, let's use AI to do natural language to Python or SQL. And so there's like whole kind of like, you know, competitions where people get like, you know, like fine-tune models or write prompts to kind of generate natural language and, or like from natural language, generate SQL, or whatever, Sui bench and so on. If you look at the code that gets generated, it's just clown town. Nobody is able to understand that. Nobody is able to maintain this. So we're just creating noise, we're creating garbage. So I think this is a dead end as well. So I hope I don't insult anybody here, but if this is what you're doing, I think you're wasting your life. So here's the real problem. If I look at traditional language, first of all, they are designed for developers to write, and maybe not even for developers to write. It's more for von Neumann machines to execute. We want to say like, oh, my language is designed for other humans to read, whatever. It's wrong, right? All these languages make compromises such that we can make them run fast on von Neumann machines. The other thing is the semantics are too complicated to mechanically reason about correctness. I visited Krista Lopez at UC Irvine yesterday, and she has been like, you know, doing some interesting work to use an LLM to generate Daphne and to generate like loop invariants and pre and post conditions. And oh boy, like I grew up in the Netherlands, Dijkstra country, and we had to do that kind of shit, loop invariants, pre and post conditions. And it's like, you know, like 50 years later, and it's still as painful as it was back then. If you have to do anything more complicated that deals with arrays, you have to like write all kind of weird formulas with indexes and so on. And even the simplest programs, like, you know, the specification is much harder to write than the actual code. So even with AI, I don't think this scales. And the reason is, I think, that the languages are too complicated. And the languages are not designed with automatic verification in mind. And so what do? We write tests and so on. But of course, tests are not really good to create correct software. And I will tell you a little bit more about that later. And then the same thing as I mentioned for these low code, no code. Languages like Python are general purpose. They're not defined in terms of the domain abstractions of the user. Haskell people will say, but we can write DSLs in Haskell, but then you're stuck with Haskell and like people's brains are going to explode. And then the last thing is that most programming languages require complete programs to execute. So you have to create a full program with all the dependencies, then you have to compile it, run it. Of course, I know people here are trying live programming and whatever, but I think the majority of the programs, it's like a very slow compile, edit, run loop, which is not great for the use case that I will show in a few slides. So traditional languages also just disappearing. If that's your job, forget it. Better look for something new. All right. So why do I say that testing in this new world is kind of useless? Well, people talk a lot about AI safety in the abstract. Oh, the AIs are going to escape, they're going to do bad things to us. I can go to the library and get a book how to build a bomb, but if the model tells me, oh, this is really bad. I think this is all very abstract. but we forget what is the concrete danger. Everybody that here has got, like, done code reviews, you know that if you don't want to have any kind of like comments from your reviewers, you just submit really big pieces of code that are really complicated, and then people will just say, okay, sure, I accept it, right? So now imagine that the model wants to do something sneaky. They want to put some backdoor in your code to send information back to some like nation state. So what this model will then do, when it generates code, it will generate really complicated code. And so nobody will actually look at the code and say, oh yeah, it's okay. And the other thing, you can say, oh, but now we can have the model generate tests. Of course, the model will not generate any test that exposes the backdoors. Right? And so I do think that if we're going to rely on models to generate code and generate tests for us, it's really dangerous if we rely on traditional mechanisms to understand that code and to make sure that that code is safe. Now, if the end user is going to generate code using a model, they don't even understand what tests are. So my guess is that, or my thesis here, is that formal verification, automatic formal verification, is the only way forward to create safe AI. So if the model is generating code, it should also generate a proof that that code is correct. Of course, this is not a new idea. This is proof-carrying code, which was invented in the 90s. But I think time has come to get, that proof-carrying code will finally become useful and practical. And the way to make it practical is to design the language such that it's amendable to formal verification. So you have to keep the language simple as possible such that you have a chance to do automatic verification. And with Python or C++ or Rust, all bets are off. You're not going to make that work. All right, so what am I proposing? Well, again, this is like some old idea from like the late 80s. And this is the programmer's apprentice. And I just replace programmer with knowledge worker because we're going to eliminate programmers. And so the idea is to provide every knowledge worker with an apprentice, a computer program or like an AI that will help them do their job. And now I really like the word apprentice, and I don't like the word assistant or agent or co-pilot, and for the following reasons. If you think about assistants get it feels like something that's assisting you with existing processes. And if you look at a lot of the big tech companies today, Microsoft, GitHub, Google, what they're trying to do is they're trying to add AI to the existing tools. So Microsoft is adding Co-pilot to Visual Studio. Why? Because they want to keep you to use Visual Studio and they want to keep you doing AI. But that's not the way forward, because what we want is we want to build new tools. We want to create a new world that is AI first. So I do think that these co-pilots are holding us back. And if you think about an apprentice, this is something that kind of learns with you, kind of that you have an emotional connection with. And so I really prefer this kind of notion of an assistant. Now then there's two things that I think you need to create a good apprentice, and that is search and code. So a lot of these if I look at these AI suites, they don't bring in shared context with them. So if you're employing an AI suite into your company, that agent needs to understand the context, right? It needs to understand what are the coding rules For example, at Meta, nobody writes code comments. And now if you bring in like a SWE assistant or a co-pilot that's going to write code comments in the code, it's just like looking kind of crazy. It also needs to understand what are the special libraries and so on. So there's a lot of context that needs to kind of come in. And that's like, you get that via search. And I'll call that like you need the nouns. You need the nouns to get like understand where you're coming from. And then the apprentice needs to be able to do tasks. It needs to get like perform actions. And these have to be domain-specific actions that are kind of like specialized for the user. And let's call them verbs. And now if we have nouns and verbs, then we can create sentences. And this is how the apprentice can work. And the way I envision this is that for every person, over time, the apprentice will create like a completely person-specific language of verbs and nouns. Think of like, you know, if you would take A/B testing to the extreme, and like, you know, that everybody's like applications would completely morph via A/B testing to the thing that's optimal for them. Of course, the big tech companies don't want you to do that because they want Instagram to look like Instagram for branding. But maybe I want my Instagram to look completely different from Gilad's Instagram. I don't even know if he uses Instagram, but so then that's easy. But anyway, so I do think that a lot of this kind of like the big tech is holding back progress in this area. All right, so let's like dive down now a little bit. So what I've been working on is two things. It's a language called Universalis, which is a language, and Automind, which is a runtime. And these are kind of like a runtime and a language designed for an AI-first world. And it's done by kind of like, I think, an interesting analogy. So first, let's kind of think, what is an LLM? Right, so the way I look at an LLM is kind of a database of compressed world knowledge. So for example, I can ask the LLM, what is REBASE? And stored in its weights is the knowledge of what REBASE is. Namely, in Git, REBASE is something that kind of like, you know, that lets you combine a series of commits in some way. So that's a kind of like LLM as a database. Now, and so think of that as ROM, right? The weights of a model, that's like a ROM read-only memory of a computer. Now let's ask another question. Like here, if we want to say, what's the current temperature in Pasadena? What we can do is we can put that fact in the RAM, in the context of the model, and then we can ask the question, and now the model can look up that fact in its RAM, in its context, and give us the answer. So context, the input context of a model, is very much like a random access memory. Now, this is maybe a little bit crazy. If you look at RAG, you've probably heard of RAG, Retrieval Augmented Generation, that is exactly like virtual memory. So if you ask, what is the REBASE conference, what the implementation around the model will do, it will go and search in secondary memory, get the facts, put it in the context, and then have the model answer the question. That's exactly what virtual memory does, right? You get the right information out of secondary storage, put it in RAM, such that like your program can access it. So RAG is just exactly the same as virtual memory. So do you get the feeling? These models are not that different from traditional von Neumann machines. There's like a one-on-one mapping for every concept that we know into something in this new world. Let's look at another thing, tool invocation. So say that we want to say, what is 100 Fahrenheit in Celsius? Because I live here now for 25 years, I still have no clue how Fahrenheit works. So if you ask the model, what is 100 Fahrenheit in Celsius, you will see that it gives you the answer, and there's this little thing here. If you click on that, you see that it has executed a piece of Python that does the computation. Now I can go off on another complete rant about like how is it possible that Python surfaced as the preferred language for these LLMs. I feel super sad about that, but hey, it is what it is. But anyway, so this kind of like these tool invocations, that's like the instruction set of this neural computer, right? It can execute things. It can take data and kind of like, produce new data. Now there's one rabbit I need to pull out of my hat, because I want to get like, if we have a neural computer like this that has ROM, RAM, virtual memory, instruction set, we need to have like an assembly language, an internal language for that kind of machine. And in order to do that, as I said, like I need to pull one rabbit out of my hat, and that is to model instructions as predicates. And the reason I do that is that these instructions or these kind of tools can be another call to another LLM. This is what people call multi-agent systems. I find that kind of like amusing, because if you write a Java program that uses 2 objects, you're not saying I'm writing a multi-object program. But if you write a system that uses 2 LLMs, people say, oh, I'm writing a multi-agent program, look how cool I am. It's just fucking insane. Anyway, let's pull this rabbit out. How long do I have?
10 more minutes.
10 more minutes, great.
Including question time as well.
Good. So yeah, so let's pull the rabbit out of the hat and say tools are relations. So think of this like I have like a relation convert Fahrenheit to Celsius. I have a relation file between file and content, between city and weather, or between like a prefix and a prefix where I predict the next token. If you model these things as relations, you don't need monads either, right? Because read file content, the next time I read the file, the content might be different. So you don't need like, the IO monad. It's just like a non-deterministic thing here. All right, so that's tools as relations. And now, code generation, generating these programs is really just like branch prediction. If you look, what does a branch predictor do in a traditional CPU? Given the sequence of instructions executed so far, it predicts the next instruction. Now, instructions, we've replaced instructions by predicates. So given a conjunction of predicates, what does the LLM do? It generates, it infers the next instruction, the next predicate to call. And so, really, generating these programs as sequences of predicates is just the same as branch prediction. So the LLM itself is like a branch predictor in the traditional computer. And then chain of thought, which are sequences of tool calls, is really the mentalese or the internal language of LLMs. So the primitive tools are facts, and then you can chain these things into larger goals. And then just like in Prolog, what you can do is you can give a name to a sequence of clauses, which becomes a horn clause, and that creates a new verb in the vocabulary, and that's how you build these domain-specific vocabularies. So derived tools are horn clauses. So like I know if I have tools to get the geocode of a city, to look up the weather at weather.gov, and then to get something from a URL, I can now define the predicate to find the weather in the city just by the conjunction of these tools. And this is what the model will generate for me, given a natural language query. Some people that like fancy words say, this is neural symbolic computing. I think it's just freaking generating Prolog from natural language. Now, you can ask yourself, do I really need the full power of Prolog? And the answer to that is no, because in Prolog you have logic variables because you want to run things backwards and so on. In this case, I always execute things from left to right, so it's really more like attribute grammars where things just flow. And so in the implementation, you don't need logic variables. All right, summarizing, LLMs are neurocomputers. And here's the the mapping. I think this is pretty neat. So everything maps one-to-one. And then there's one more thing. As I said, I need to keep the language simple. And in Prolog, people, if you want to do repetition or so on, that's typically done using recursion. But I don't want to have full recursion in the language because otherwise it becomes too hard to reason about. So what we do is we just add support for bulk operations. You can map implicitly by lifting predicates from the elements over values or over lists. And I add monoid comprehensions, just say SQL to it, such that all the recursion is captured in these special operations. So let's give here an example. And then the other thing is that the programs are embedded in an explanation. So if I kind of ask a question, given a set of players, select the best team for the next World Cup soccer. I'm using, instead of uppercase letters, I'm prefixing variables with @ and now the model will generate something that looks like natural language, that has inside it these kind of little snippets of Prolog, but really this is just doing group by and kind of aggregation and so on. So what is my vision? My vision is to build the next Sun Microsystems for the AI era, right? Because not only does the virtual machine map to the virtual machine of the past, but you need the complete ecosystem as well. So it's write once, run anywhere, prompt once, run anywhere. So the kind of my runtime extracts over the kind of different LLMs, and of course you need at some point. You need some repository of kind of facts to do code sharing and so on. But I think instead of having a measly developers, we eliminate them, and suddenly we get a lot more users. Let's dive now a little bit into the implementation. The implementation is kind of typical multi-agent thing. So in order to, when something comes in, there's models that look at the outputs of models and do all kind of complicated things. In order to do this virtual memory thing, this RAG, you need to deal with documents that have structure. So what I do is I parse documents into ASTs and then index them based on the ASTs. I've never written so many recursive descent parsers in the last few months. And then I accidentally reinvented intentional programming because I was trying to make the model generate concrete syntax, but that turned out to be really hard. In the demo, you might see this if I have time for a demo. But then the models came out with guided generation, where you can give it a schema of JSON, and then it will generate the output according to the schema. So what you do is you just define the JSON schema for your AST, and you have the model generate AST, and then I print that into user-facing syntax. I generate Kotlin for execution, and then I generate Daphne for formal verification. So let's do the last few minutes to talk about verification. And this is my new slogan: bugs don't vanish with tests, only proofs ensure their absence. And so what we want, or what I'm doing, is I'm leveraging Daphne for correctness and safeness. So if you can, ask a question, and this is a whimsical example, right? So I have an apple costs $P, the price is raised by X%, how much does an apple cost now? So this is a question. The model will generate here a program that gives the answer. Now what you can do is you can ask the model as well, what is the precondition for this code? And then the model will generate a precondition. And since it says here that the price gets raised, the model infers that, oh, the price of the apples must be positive and the percentage must also be positive. All right, so this is not like the kind of precondition that you would have in traditional coding. It's more for something that the kind of normal user said, oh, this is kind of reasonable assumptions if I ask this question. Same thing here is the post condition. Often when you write like Daphne or you use pre and post conditions, the post condition is just another phrasing of the actual algorithm. So in this case, the real post condition should somehow redo this computation, which is nonsense. Because really what the user wants to know that the new price is greater than the initial price because I've raised the things with a positive thing. So instead of having full correctness, you just want to have like something weaker that gives the user the sense, oh yeah, this is reasonable. And so that's I think still something that I'm investigating, where you don't want to have like full correctness, but you want to have something that gives the user a sense that the code that is generated is reasonable. And of course, if it's really critical code, then you want to turn up the dial to get full correctness, but in most cases, this is fine. All right, I don't know if I have time for demos, but maybe it's time for some questions.
Yeah, let's thank the speaker. We are running out of time, but let's take a few questions.
Yep.
My question was, could you show us a demo?
I can show you a demo. I'm happy to give a demo afterwards. I think I have time for it, but yes, I have this thing up and running. It's not like like vaporware. It's right here on my computer.
So very thought-provoking talk. So I'm not sure I agree with your analysis of why hardware scales, and I think it has to do with a difference in how we specify problems. I mean, hardware teams are actually pretty complicated. There's thousands of people that work on CPUs. I think they have very good specifications, and they have like ability to break down problems recursively and to have like input-output specifications. I think the problem in software is that we can't make up our minds. We don't know what the layers should be. You showed JVMs in your diagram of things. Those have gotten a lot faster over time because they have very constrained input and they have a very clear job to do. And I think that part of the problem in software is that we're not very good at defining what the jobs of different pieces are. So I think it really is a specification problem too.
Yeah, so maybe like we're violently agreeing, because I think we need to constrain our language that we can like express our code in such that we can reason better about it. But I do also think that the scaling of hardware that I pointed to is that I can I can cram twice as many transistors into something, and it will go maybe twice as fast or become twice as powerful. I cannot just cram twice the amount of developers on the problem and then expect that it will be solved twice as fast, unless you use Agile, right? That's like twice the work in half the time. But I can walk on water and turn water into wine as well. Right, question back there.
Thanks, Eric. Thought-provoking talk. So I guess my question is that the details of the vision you're pursuing is quite different from what a lot of the sort of major labs are doing. So the target is the same, which is knowledge workers and not programmers try to sort of make their lives easier. But I think especially with things like say anthropic computer use and other such demos, the vision that they're following is that for a lot of tasks, there is no program to be written. Like if I want to get a bunch of email addresses off, say, LinkedIn, I have no idea how to write that code, and no expert could even do that. Instead, it's better to just have a model directly interacting with the computer and doing that. So it's sort of not just eliminating programmers, it's actually eliminating programs as well, I would argue.
That's a very good question, and I would say what I'm proposing is not that far off from what they're doing, because in some sense, when I ask this kind of the thing that can kind of click on the website to do something, that is like a verb, right? So that is the thing that I want to achieve. Now imagine that I want to do another thing after that. Then I want to give that a name too, and now I want to say combine these two things. So I think the kind of being able to kind of automate certain parts of the things is only the first. That's the leaves of the things. But now, if I want to reuse that, if I want to do it again, you don't want to kind of rephrase it again. So that's where you build this domain-specific vocabulary. So I think they are kind of mutually enforcing. It's not either or. So these are the primitives. And again, what I mentioned in the beginning is like, a lot of the things that we see, the primitives are not in the kind of realm of the user, right? If you look at low code, no code, but these things, like if I can just tell it, like go and do this and it will click, that's at the level of abstraction of the problem domain of the user. But now you want to capture that and then kind of compose above that. All right. Thank you.
I think it's this side. It's this side.
Oh, is it on this side? Yeah. I keep. Okay. Let's see what happens here. And there was some trick to this option.
I can do it.
Yeah, yeah.
Do you have notes for your slides, or
No, just don't touch the slide. Just do that, and we'll be fine. Okay. Then we don't need that. We can put that away.
So our next speaker is Gilad Braka, and going to talk about apps and their stores.
All right, a few preliminary remarks. First of all, whoever scheduled me after Eric, if there is any justice in this world, you will pay for that. But other than that, you will note that there are two side-by-side displays of these slides, and that is not an oversight. That's deliberate for reasons that should become evident very shortly. So this is a history, an alternate history, but it is, as they say in the movies, based on a true story, as you'll see. So whenever you deal with a history, there is a question of where does history begin? And in our case, it's going to begin at the end or close to the end. Not quite the end, but the end is in sight. And what do I mean by that? What is the end that I have in mind here? So you might have noticed that these two presentations are tracking. So this is Chrome, and this is Safari. So these are two separate browsers, two separate web browser implementations, and the slides are in sync. And sync is one of the major themes of this talk, because that is sort of the end for my purposes, right? This is the end goal that I've had for many, many years, which is that my view is that things like collaboration and local firsts or synchronization of replicas that go on and offline and things like that should be the responsibility of the platform, of the programming system, not the responsibility of the individual program or application that wants that to happen in their space. And that is the story that, the history that we're going to explore here, or at least a large part of it. But we're beginning at the end because it's finally in sight, at least part of this is working. Mostly thanks to other people's work. Yoshiki's right there. But what is happening here is this presentation is a docu-app in Ample4 for those who saw the talk on Monday. So it is basically a system for live documents that this presentation is constructed in on top of the Newspeak platform. And the Newspeak ID is integrated into here. And we can, let's take the other one. We can click on the home screen, and I'll probably make those bigger because that's the thing. The slide size of this side are not the same. Is that decent? Yeah, okay. A little bigger, okay. The problem is, of course, that eventually this will get out of hand because, you know, there's not enough real estate when we have to. Well, the thing is we want both of them that way. So, yeah, okay. So, again, you can get into the IDE from here, because when you program these live documents, some things are not possible to do by just dragging and dropping, and you actually need real code. And so in this thing, you have full access to the namespace of the IDE. And this is a list of all the top-level classes, the modules in the IDE. And you can go look at them. Now, some things do not sync, and that's deliberate. Well, it's a combination of path of least resistance and deliberate. And so there's good reasons for letting individual clients scroll to where they want independently. You can debate that. There's good reasons for them to zoom independently. But it's also, some of these things are harder to do than others. But we can go and look at classes. And this is a class that deals with UI. And inside here, we'll see that they have the same class. And there are nested classes here that are individual components. And so you can browse all this stuff. And then you can go back to the root. There's a history thing. And you can do other things, right? Everything the IDE can do. So if we say want to run some tests, there's a unit test framework. And the point of this is that I'm showing you all this is not to tell you about the Newspeak IDE, but to show that, in fact, this entire thing is synchronizing, and it's working in both these browsers. And I only have one machine, but it works across the internet, across machines, and all that sort of thing. And it's actually fairly responsive. So if you open up all of these methods, right, these are the successful tests, which aren't shown by default, because no one ever cares about your successes, only about your failures. And so we can open these, and that does take a little bit, but here they are, right? All these methods open up. So generally speaking, the IDE basically works collaboratively. You can evaluate things, you can type live in a window, and you can evaluate things, and you get, object inspectors, they work, right, that sort of thing. And so all of this stuff is not because I went and built a collaborative IDE. That's the point. Because this IDE has been around for a while. The presentation tool I built fairly recently on top of it, and none of this has ever been collaborative or was made collaborative, and no source code was harmed during making them collaborative, right? This is the same source code as the non-collaborative version. It's the same bytecode as the non-collaborative version. Not one character has changed. So how is it collaborating? It's collaborating because the platform is doing this work, and that's the idea. Now this is an early experimental demo, and if anything goes wrong, it wasn't me, but this is not ready for prime time by any means, but it is basically showing that this is plausible, and this is all utilizing the work of Croquet that people like Yoshiki have been doing, and if you saw his talk on Tuesday. But it's very different from the way Croquet was intended to be used, and in fact, I'm not sure that Yoshiki approves at all of what I'm doing. So the way the Croquet system is supposed to be used is, right, it's in JavaScript now. It's a descendant, of course, of the original in Smalltalk. But either way, you write your collaborative program, fully aware that you're writing a collaborative program, and you make calls out to Croquet, and you subclass Croquet classes, and you do things, and it's design, and you make this thing collaborative on purpose. You don't just take something that was never designed to be collaborative and flip a switch and suddenly it is collaborative, which is what I'm doing here and rather proud of. So we're doing something different here, and I don't necessarily have a lot of time in this talk to go into how I'm doing it, but it is something that potentially you could do in other systems, but it is way, way easier to do in Newspeak. And so the underlying platform, for example, the UI, the built-in UI library is taking care of this. So you basically swap out in Newspeak one platform object for another. The platform object that has the collaborative UI will make sure that all the regular applications unchanged will run collaboratively. So that's kind of the core idea here. The end game is to make synchronization and to go beyond what Croquet does, because the original motivation was not necessarily this real-time live collaboration, which is very nice, but the local first, the ability to go offline and go online. And that's what I'm going to talk about a bit more. So if we go back to our slides, and maybe make them a bit smaller again. Right. So we should now start and go back to the beginning, because this is part of the end or close to the end. When this works perfectly and is solid, and we figure out the local first stuff, that is the end game. And you know, if I'm lucky, in a year I'll come back and have something more. But this is also the end of the happy part, right? This is a story, and it is not, and I'm hoping it has a happy ending, which is what we showed you, where all of this will work and be really cool. But in general, it is not a happy story. It is a story of you know, industrial woe and short-sightedness and bitterly looking back. That's what I'm here for. So where does the story begin? It is a tale of folly, and it begins appropriately on April Fool's Day 2004. And the particular folly we are concerned with is this is the day, very appropriately, that Gmail got launched. And I, early on, was very enthusiastic and was an early user of Gmail. And I very, very quickly, within a matter of 30 minutes or so, you know, went through, you know, grief, denial, disappointment, et cetera, and decided this is not what I want. I was, on the one hand, immensely impressed by, wow, you can do this in a web browser. I had no idea back in 2004 that this was plausible. They're very clever people. But on the other hand, it was also very clear that it is not what I wanted. And this led to some thinking which resulted in a vision of what I wanted, which is this thing that I have talked about in the past multiple times, and some of you may have seen these talks or heard about them, this idea of objects as software services, with this idea of orthogonal synchronization, which interpreted, there was a more narrow and specific interpretation of that originally, but basically the idea being that the platform or the programming language will take care of sync for you, right? And so, you know, that idea, the first discussion of it publicly was in the Dynamic Language Symposium in 2005. I gave a keynote 19 years ago. And then that one was not recorded, but there are recorded talks for anyone who's interested. You know, talks I gave at Google, at Microsoft Research. There, you know, look at my website. But the earliest presentation of this has never been shown publicly. It is this presentation, and now to show you that this is a sad story, we're going to go to PowerPoint. And after that, when we come back, we'll also see some of the bugs in this system. So, PowerPoint. Oops, why are you doing that? Okay, it's showing for you, good enough. So this is this is a PowerPoint, an original PowerPoint from 2005, period styling, unchanged, that I had, that was used, was shown to venture capitalists. One of the, as I tried to get this idea off the ground, I did several things, and we'll talk about them, but one of them is with my friend and colleague Johan Kashai, we actually tried to raise money to do something commercial with this thing. And these are the slides that we used. At least this is one set of those slides. And so we were calling these things rich internet apps. There wasn't really good terminology back then. And this is a space that's divided, as you can see. There's enterprise versus consumer. This is little applets versus applications, and desktop and mobile, right? And this is of course for VC. So this is a bit of a marketing spiel, but again, this is an industry academic collaboration. So some industrial waste should be used. So anyway, what the state of affairs back then was mainly the big players were Java and .NET, and they're focused on enterprise. And there's very little elsewhere, and the thing manifests on the desktop. That's where the UI shows up, right? And there's nothing in mobile. When you look at mobile, well, there's very little, but there was something. Anyone remember J2ME? Right? Yeah, okay, yes, I know the old guys remember, but so Java on the mobile device, believe it or not, that was a thing back then. And it ended up where it belonged. And you know, but we had to illustrate the space. And what we were interested in was this red zone, which is entirely in consumer, mostly in mobile and dealing with real applications. So applications for consumer on mobile, you begin to smell the App Store that's in the title here. So we were interested in portable, personal information, things that centered around your basic data, your personal data, addresses, contacts, calendars, etc. And we argued that there would be a lot of add-on applications that would stem for that, tools to make that easier and things like that, which was a bit of a stretch back then, right? Because envisioning what those might be, I'll show you one example of this as we go along. The other thing that's important was this is a slogan for this vision: always available, always up to date, which basically means that yes, it's available everywhere, like a web application. You can get it through the network and run it on all your devices. And the other thing is that it works online and offline, right? This is very much in line with the modern local first movement, though there are differences, right? And the idea is that when you get back online, it synchronizes, right? Automatically. You don't have to write it. The platform will do this. That's the kind of idea. And the result of that is also people wouldn't have to worry about versions. That's something I liked about the web thing, that there's no old versions that you can go and ask the consumer, what are you running now? You're running whatever's on the web page. And that meant that that stemmed from the fact that we're synchronizing not just the data, but the program. So there's always, we're always up to date. Okay, I'm kind of gonna zoom through this so I don't end up over time. This is probably something we can skip, but here's an example. And this touches on another one of the points of this talk, which is sort of the siloing of applications, which is closely related to some of the stuff I mentioned in my talk on Monday about live documents and transclusion and stuff. So what you have here, right, someone has a calendar, and they have a flight on a particular day. Now the first thing is that the flight should not be just saying, oh, I have a flight on that day. It should actually be a live thing that you can actually go and click on and explore your itinerary and everything, right? And it should be there in the context of your calendar. And if you, say, decide that you'd like to know what the weather is at your destination, you take a widget and you drag it in there. And this was inspired, by the way, by Morphic and Squeak, the idea that the way that you can easily compose these things, but also with semantics, not just the visuals. And the idea that the weather button would be a thing that would look at its context. There would be an API to get at your context, and it would look for dates and times and places, and so it would know where your thing is. And so the idea here is that these are apps that are customizable by the end user interactively, say on the desktop, but then this thing will continue to work on your mobile and so forth. And so again, no siloing. This is another more hand-wavy thing that I'm not sure we ever figured out how we would do, but something to do with the templates for this thing is that we would then infer that you probably wanted this weather button in your other calendar entries, right? Now this is easy. Now we just use Eric's language and it figures it out. It knows everything. But at the time, that's a hard thing to do. And so this was also part of the vision where user control applications and no siloing. So what's important about it? Yeah, synchronization. I keep emphasizing that. Basically, the platform would do this for you, and yeah, it would support collaboration. We talked about that. I don't think we did not envision at the time quite such real-time collaboration, which is weird because I knew about Croquet at the time, but never put two and two together. So anyway, here's how it might work. We have a user here on one side, and that user has two devices right over here. And this is the service, essentially. And what could happen is, this is the App Store, basically. You upload a new app to the App Store. Then the user connects and buys the app and downloads it. And so it shows up over here. And the user continues to do stuff. And maybe he's working with another app, and he's got some data here. And later he syncs up again, and that data finds its way to the service, which is not just an app store, but is also the backup for their data. and the site where this data is stable so you can collaborate and do all these things. And you know, later on, the user connects from a different device, and they sync up, and they get the new app that they had loaded from the other device, and they get the new changed data. And so this is how things are going to envision to work. So yeah, again, orthogonal synchronization. This is probably the first written reference to that phrase. And it's tied to, of course, orthogonal persistence of saving the state. And so in that sense, we're talking not only about app stores in the sense of store in the sense of shop, but store in the sense of storage, of memory. And what else did we do? There was, yeah, program equals data. Yes, this never gets old, and we advocated for treating the program as data that needs to be synced as well. And of course, that means that the apps would update when there are new versions. And this, of course, is dynamic program update, and doing this without shutting down your program and rebooting, right? A small talker always will be. So that was kind of the vision that we had there. Yeah, capability-based security was also a thing, right? So this eventually manifested in Newspeak as the OCAP language model that we use. Yeah, portability. I was one of the people who came up with the acronym WORA. I'm sure there's differences of opinion who came up with it, but write once, run anywhere at Java. It never worked for Java, but I knew it could work because it worked for Squeak, which ran bit for bit compatible across anything, right? So it can be done, could have been done, and we were advocating for that. Yeah, we can skip this, kind of repeats this, you know. I do want to show you this slide because that's the plan. What is the business proposal here? Sell apps. It's an app store, right? And other variations of this were, you know, different models business-wise of who you'd work with, but they're somewhat interesting. So one was, yeah, partner with Google, and Google hosts this thing, right? The Play Store, but this is before the Play Store, before Android, before Chromebooks, before the iPhone, before all of this stuff. Another possibility, yeah, the mobile carriers, they were interested in this because they were kind of being disintermediated. They never succeeded, but they were certainly open to it. And the last option, yeah, try and get Nokia to use this stuff, right? So remember Nokia? Nokia was the premier manufacturer of mobile phones. Apple didn't make phones. Google didn't make phones. None of these companies did anything with phones. But the idea of having this system on in mobile devices sold through the phone manufacturer, well, gee, that might work. Who knows? But anyway, yeah, you could do all of the above. And that was our presentation for the VCs. And now we'll go back. And hey, this is why this is still broken, for reasons that I don't have time to get into all the technicalities of things. But if you go offline, then things stop. That I think I know how to fix this, but this is why this demo is so delicate, because if the internet connection here went, then the whole thing would be shot. Full disclosure. But somewhere here, we do have a non-collaborative. This is the same presentation running on the non-collaborative Newspeak platform, so it'll work. And we'll make it a little bit bigger. Maybe we can even make it full screen. Yeah. So this is where we left off. And, you know, the venture capitalists did not buy this. My entrepreneurial skills are not what one might hope, it turns out. But one of the things that one of them said, you know, is still burned in my mind. They said, we won't do this. This is a platform play, a horizontal play. We don't do that sort of thing. But the next thing he said is, Sun Microsystems should do this. And I was working at Sun Microsystems, and I think, yeah, you don't say. How come I never thought of that? Of course, I had thought of that, and so this is another tale of woe as to how this went about. So you all know this is Duke. This is a beautiful picture that James Gosling sent out when Oracle acquired Sun. And yeah, so Duke at the grave. But let's look at Duke at the cradle. Where was Duke born? Duke was born. Let's make sure we don't have sound, because the sound is annoying on this thing. But this is a video James made about the Star 7, this mobile device that was the sort of the origin story of Java way back in the early 90s. They built this mobile device, and Duke was this kind of mascot for it, as you'll see in a moment. See, there's Duke. And he was the Clippy for the Star 7, right? And then later he got demoted to just a dead mascot because whatever. But Java started on the client, and then there were applets, right? Java was supposed to run in the browser with applets. It was supposed to do what JavaScript does, right? But it didn't for various reasons. Some of them Java's fault, that it wasn't well suited, and some of it was just ahead of its time, and things were too slow and whatever. But Sun had been looking at, it started on the client, and eventually they switched catastrophically to the server. But when I brought this idea to my management in Sun, the people at JavaSoft that had been trying to make the damn thing work on a client for years, they were amenable to this because they knew that their thing would not work on the client, right? They knew that didn't work. And I basically told them, you know, you remember how I got here with the Smalltalk engine that you bought so that you could make your damn language run fast? And so that became the hotspot VM. So we still have that lying around somewhere, buried, and that is a great client. That comes up instantly, that has native widgets that respond. It doesn't have AWT, it doesn't have all the genius UI things that you came up with. It actually works, because it's Smalltalk. And what we can do with that is, you know, you're already at the stage where you're updating JVMs, which are everywhere over the wire, that had just started. And, you know, that whole runtime is a couple of megabytes. Just smuggle it in as an extra, just push it out, and then you'll have a client runtime. And then we'll do this Appstore. And the higher up at the medium levels that I was talking to, well, this seems interesting, but of course we don't have the authority to do this, et cetera, et cetera. So you need to talk to the higher ups. And what do you think the higher ups told me? You know the graduate, this line about plastics? One word, son, thin clients, right? So this is a Sunray. At the time, this is, I think, the picture I found, I think this is a first generation Sunray. They were on the second or third at the time, but they had just released a new Sunray. A Sunray is basically a very expensive glorified dumb terminal. It is an IBM 3270, essentially a thing with, if you know what that is, it has a coax cable that can send enormous amounts of data, but ends up displaying next to nothing on the screen. And that is, and just the industrial design team that made this nice purple plastic box probably would cost more than it would have cost them to productize Strongtalk. But that was the state religion. And so they would not hear of this because what you're proposing is a thick client. That cannot be. And so that sort of ends the tale of woe in a way, because those were my attempts to get this off the ground. And then we started the Newspeak project. That's a different story. And we got somewhere until the crash of 2008 ended that tale very sadly, because otherwise we might have made it work. So in the end, the App Store we wanted, which could have been, would have let users customize their apps, let them compose freely, no siloing. They would run online and offline and synchronize, including the no versioning. They would do dynamic live update, and with capability-based security. And yeah, it never happened because I don't have any skill at selling or convincing people, and that's my story. Thank you. No questions? That's great.
What were the more specific reasons why you didn't like Gmail?
What I didn't like was I wanted the capabilities of a native client. It just felt that it well, at the time it didn't work offline. Like if you use Thunderbird, or God was mother, it's an email client running everything. Your email's there. If you at the time you don't have an internet connection, you can get on the plane and look at your email all the same, right? You couldn't do that, right? That sort of motivated this whole thing. That's what motivated the local first movement that started many years later, is the fact that, you know, if your internet connection is slow or intermittent or insecure or non-existent, or if you have a connection but your cloud provider is down because they crashed or they have a denial of service, a million reasons why you can't get to that thing, you are up the creek without the paddle. That's the fundamental thing. I forget, but it just felt wrong as a, you know, UI-wise, and everything felt lousy, and I said, yeah, and besides that, it didn't even do search well, right, for the email, but that's separate. But really the reasons why I felt that, yeah, it's amazing you can do this on a web browser, but I needed to do other things that wouldn't do. Ben.
So I was there at the funeral of Sun, and I feel like Sun was a little bit spoiled because the fish were jumping in the boat, and so they were focused on building the biggest boat possible. And
is the microphone not working? I think it's working.
Can you hear me?
Can you ramp it up? Because in the back they could not hear you.
So my comment is basically, it seemed like the economics of Java were such that it was selling servers, and Sun maybe didn't have the foresight to want to branch out to other things. It seemed like it would have been possible to fork Hotspot and use it for different things, but that didn't happen. Do you have any insight into why that might have been?
Well, certainly there was not a lot of imagination there. So you didn't need to fork Hotspot to do this, but you know, in this particular case, but other things perhaps. But yeah, I don't know that I have insight into why, but they were, you know, the management they ran the company into the ground, right? There's no question, and it was just with that kind of thing, there was no hope, really. I mean, this is a long story that we could get into about personalities, which I'm not going to discuss here, but I don't have insight except it was badly run and it lost its way. Eric, you had a question at one point.
Yeah, so you make it sound as if like this thing was like super easy to build.
No.
But now
Very
you
hard
have
to
like
build.
you still had bugs. So were the VCs right or wrong?
The VCs were wrong for the simple reason that, you know, whether we had a business or plan, we would have an app store at eventually of some sort, even if it did half of this. Then someone would have bought it as a technology transfer story, right? Because once Jobs got on stage and said, there's an app store, you know, all the lights would go on, and if you had anything that could do any part of that. So the VCs were wrong, but of course it's not that easy. This thing that I just showed you is something that I've cooked up in the past couple of months in my spare time, because all the hard work is what Yoshiki does and Vanessa have done, except for this idea of that I can slide it into the platform and not make people do that. And so, and it has, sure, of course it has bugs. Anything I write has bugs. That's why I have to work with, someone said work with people smarter than you, Alan, whatever. I don't know how Alan finds people smarter than him, but I have no problem finding people smarter than me. So, sure, that's why someone should do that. Now this, at the time when we had the slides, this was all vapor for the VCs, right? None of this worked, and we had only the haziest idea how to make it work, right? We eventually got the object capability to work. We had a fast VM, which we didn't use, but we could have gotten to that point. The synchronization is a hard story. I mean, the key thing here was the insight that I could use Croquet, which I could have used back then if I wasn't so distracted by their shiny 3D stuff that I didn't even think about their synchronization model. And that still wouldn't have solved the offline part, which is the hard part. And there's been, I don't know how many years now of CRDT research where this is finally in reach, right? So now I can see how I can finish it. We had thoughts about how to do it, and maybe we would have figured it out or not. But yes, it would be, this required VCs. That's why we needed VCs. We needed a team of smart people who would probably work on this for several years and so forth. But the VCs were not right. Dave? I've looked at Unison, and I'm not that's a long discussion, but I'm not necessarily a fan. Yeah, yeah. Are we done?
Well, thanks a lot.
Thank you very much.
Okay, so we're going to start the next session. So it's my pleasure to introduce Lennart Augustsson. He's at Epic Games, and he's working on Verse, and he's going to tell us a little bit about it.
All right. I guess I need to stand here. Okay. Yes, so thank you for inviting me to talk about Verse. There is a lot of people involved in this. Not all of them at the same time, but you might recognize some names on this list. So, what is Verse? Well, Tim Sweeney is the founder, majority owner, and CEO of Epic Games. He's also a programming language nerd, so it's quite nice to work for a billionaire who likes programming languages. And so he's been thinking about this language for like 20 years. And then I guess he decided he needed to hire some people to help sort out some theory bits and implement it and so on. And when you're a billionaire, you can do that. So yeah, so here's a bunch of things. So our job has been to try to extract from Tim's brain what Verse really is, because it's really only been in his brain. I mean, it's very well thought out, and we have our weekly meeting with Tim, and every time we have one of these meetings and we suck this out of his brain, we end up like this. There is a lot. So it's a functional logic language like Curry or Mercury. It's declarative. I mean, a variable stands for a single value and it doesn't change over time. There are assignable variables as well, but the main thing is more sort of the pure ones. It has lenient evaluation. I'll come back to that. So it's but in between strict and lazy, things don't happen necessarily in the order you write them. The compiler can choose which order to do things, but at the same time, it's not like lazy. Everything will get evaluated eventually. It has a very unusual static type system where types are first-class values, and there's also an effect system. So there's so much to talk about Verse, so I'm going to try to get through some of the unusual bits about Verse. So it's interesting to see what choices someone who is not in the traditional programming language sort of group does, like, because Tim has designed this language and everything fits very nicely together, but some of the choices are unusual. Just to give you some quick flavor, I mean, it's nothing strange about the syntax. It's like you could imagine integers. There are tuples. Verse doesn't distinguish between tuples and arrays. They are all sort of a number of elements of things. They can have different types of the same type, which is a nightmare for the type checker. So anything where you have a variable that follows, but that is followed by a colon, means that you're doing a binding. So for instance, you can say x colon equals 3 and then x plus x, or I mean, you see some other variations. And the bottom one, you can also say something like x colon int, which looks like it says that x is an integer. And you can think of it like that, but it means something different. But I mean, really, it means that. I'll come back to what it actually means. Y equals x plus 1, and then you can say x equals 3. And that equals there is sort of a constraint on x. So the implementation will probably do this by unification. This first thing, x colon int, introduces a new logical variable, and then you say, okay, and it should be equal to 3. But there can be other places saying x should be equal to 4, and since it can't be both equal to 3 and 4, that means that this could fail. I'll come back to that too. Functions, lambdas, nothing remarkable. You look at this, you think you know what it means. It actually means something different, but it still does the same thing as what you think it does. That's the weird thing about verse. Yeah, conditionals, recursion. Again, you can read it and think you know what it means. Some slight variations here. You could say factorial of 0 is 1, and factorial of n, where n is a positive integer, is something else. Or you could say factorial of 0 or 1 is 1, and n is an integer where n is greater than 1. You can say that too if you want to. And if you can see here that I have carefully made sure that these two clauses don't have overlapping domains. You can, but I won't get into that now. Okay, so now we get to something that it's a little bit different, because there are the other things. I mean, you can do that in any garden variety functional language. Choice. So vertical bar is a choice operator. So you can think of expressions as not yielding a value, but a sequence of values. So 3 is, of course, just one value. 3 or 4 is 2 values. There's a funny way there of writing when you want no values at all, colon false. We'll come back to that, see exactly why that looks like that. Or 1 dot dot 10, for instance. And once you have the choice thing, you could do sort of things that similar to what you can do with list comprehensions in Haskell. You can say x is equal to 1, 7, and 2. And if you say that, x is not that choice. X will take on the value 1 and then 7 and then 2. So it's the choices are not first-class things. You can't name a choice. But if you say something like this, the variable will go through the different values of the choice. So that's just like that little Haskell list comprehension there in yellow. You can nest them, and then the outermost iterates slower and in the most faster. Nothing really strange there either. Yeah, and you don't have to give names to things. You can, this thing x equals 1 or 2, y equals 7 or 8, x comma y. You might as well say 1 or 2, comma 7 or 8. They will iterate in the same order. And you can combine these freely, the choice things. And if you say something like 77 plus false, well, if false has, there are no things, so of course, trying to add 77 to everything that there are no choices, that is still no choice. You can do slightly funnier things when you have lenient evaluation. So x is either y or 2, and then y is 7 or 8. So the iteration order goes from left to right, but the data dependency goes from right to left. And this works out. I mean, I'm not saying this is a good way of doing anything, but these are sort of a consequence of how the lenient evaluation works and what it gives you. And if you try to do something like that in Haskell, that doesn't work because y is not in scope there in the first position. Oh, by the way, if you have questions, I'm happy to take questions immediately from the audience. That might not work well with the microphone, but if someone has an urgent need to ask a question, please do. It's better than saving it to the end. Okay, so now we come to another unusual choice. There are no Booleans. Instead, there is this failure or success. So we saw already multiple choices. There's more. If there's one or more, that's regarded as a success. And failing is, well, that's failure. And so when you say if E something something, if E succeeds, then we get E1. It doesn't matter if E succeeds in many ways. You only get one version of E1 anyway. And if E fails, then you get E2. And is there anyone here who remembers icon? Ah, there's a couple of old timers here. icon had exactly this. So it's not new, but it's been polished. So if something like x less than 20, that fails, of course, if x is greater than 20, and if it succeeds, then it returns the left operand. And that means that you can do cute things like if 0 less than x less than 20. So less than is right associative. So if x is less than 20 in this thing here, then it returns x, and then you compare that to 0. And things do what they look like they're supposed to do. This is another sort of cute thing that I don't know if it's good or bad, but it works. And you don't really need and an or anymore. You can just use comma, which is the thing that builds pairs. So if either of the two components fails, then of course the whole thing fails. And for or, you can just use choice. And yeah, so you can test for equality. And so we'll see how we'll do it on time, because I also said that this equals is probably unification in an implementation, but you don't really want this comparison with 0 to set x to 0. That would be weird. So there is a notion of rigid and flexible variables that you don't have to think much about it, but it's there. Yeah, so the bottom example here is a one of Tim's favorite examples. He said when he got some BBC Micro or something like that, and he was trying to write a program in BASIC, and he thought this would be the most natural thing to say. If x equals 2 or 3, then I want to do this thing. But of course, that doesn't work at all in normal programming languages. But here it works just fine, because 2 or 3 will be those two choices, and then you will compare x with 2, and you'll compare x with 3. And if one of them succeeds, then yeah, then you go to E1, otherwise E2. I think this is quite neat as well. So here is an interesting aspect of this. So if you have something like an if with a condition, the condition is a transaction. So it either succeeds and then everything in the condition happened, or if the condition fails, then nothing in the condition happened. And so normally you can't say if something happened or not. But once you introduce variables, so here we have a variable that you can assign to called x. It's a mutable variable. And in the condition you say, okay, I'm setting x to 1, and then I'm comparing 0 and 1, so that obviously fails. Well, then we didn't set x to 1. That goes away. So the whole thing there is like a transaction that either all happens or nothing happens. And you can think about sort of a more game example. You move your player, and then maybe you test if something abnormally happened, you were on the wrong side of the wall. Oh, then you shouldn't have moved the player, and that will be automatically undone. But most of this code, move player stuff, is probably written in C++. So in a heroic amount of work, not me, have done this so that it actually will work with C++. You can talk more to Sam here if you want to know more about it, or Phil Pislow if you can find him. He was here earlier. I find this absolutely amazing that it will work with C++, but yeah, it will, at a cost. We talked about choices, so you can turn choices into an array or a tuple, whatever you want to call it, and it's called for. And so if you give a bunch of choices to for, you will get an array back with all those elements reified into a concrete data type. So for takes this sort of ephemeral choice things and turns it into a data type where you can actually get hold of all the elements. So nothing remarkable. If you do it for 0 choices, you get the empty array and so on. Order matters, of course. Choices are not commutative. They are associative, the vertical bar operator, but you want the order to matter.
Excuse me?
Yep.
On the previous slide,
Yep.
why isn't the third result a tuple of a Boolean?
Oh, it's because you don't know what false means. You think you know what false means, but it's, I'm sorry, it's one of the weird things about verse. So I mentioned it earlier, colon false is the thing that gives you the empty set of choices. It's, I would not have named this false if I were in charge. I would have named it empty or something like that. But I mean, I'm not paying the bill. Yes, order. You can also go the other way. If you prefix something with a colon, there are 2 ways of writing this, but I'm only showing you this one. If you prefix an array with a colon, that means you get the choices of the things in the array. And so colon and for are sort of each other's inverses. If you do colon and for, you get back the thing you had inside, and for colon e, the other way around. And here you can see the definition of false is just the empty array. Again, I find this a terrible name, but yeah. Which means that if false is the empty array, that means that colon false is the empty set of choices. There's a slightly more general version of for, which is instead of having for and curly braces, you can say for, and then E1 is the thing that describes what you will iterate over, and the thing in the curly braces are the things that you sort of produce. So for I equals 1.3, and then you produce I times I inside. That will sort of be a for loop that iterates 3 times, and you get 3 elements in the array. So for subsumes list comprehensions in language like Haskell, because you can stick predicates if you want in there. So for I equals 1.4 and is even I. Oh, I see now that those round parentheses should have been square parentheses, but only the people from Epic will notice the difference. In a few slides, the rest of you will also know that it is a difference. Yeah. You can also have something that fails in the body, which means that to get anything at all, they all have to succeed, otherwise you get nothing. So for I equals 1.4, I less than 3, that will be like comparing 1 with 3 and so on. And 2 of those comparisons failed, and that means you get the empty tuple. So you can easily write conditions where you want to sort of filter a bit on the the domain, and then have a range that tests different things. Here's a more bizarre example. Now the body of this has a choice. So for I equals 1.3, the body is a choice of 1 or I or I plus 7. And so this behaves like you would think it does. So the for loop is sort of, you unfold the for loop. That means you get a choice of 1 or 8, 2 or 9, 3 or 10, which then in turn unfolds the way you think it should. So you can write really few characters and completely bog down your computer. Here's an example. It's something you should never write, but that doesn't matter. You iterate from, you have A is an array, and you iterate from 0 to the length of the array minus 1, and then you index into the array and add 1 to them. I mean, this is not the right way to write it if you wanted to compute this, but it's just to illustrate. So an interesting aspect is that things you bind in the condition of an if are visible in the then branch, not in the else branch, of course, because you failed with the condition so that nothing would be bound, which means you can write nice things like, if x equals, you index into the array into the ith position, if that's there, if there is an ith element, you'll get that. That will be called x, and you can compute something. If you index outside the array, it will fail, and the if will go to the else branch. So that's kind of neat, I think. So I don't know if there are other languages that has this particular feature with ifs. I mean, I wish more languages had this, because I often want to, when I write C, I often write weird C code like this, that I compute something in the condition and I need to use that. And then I always have to declare the variable outside the if, which means it has more scope than it should have. Now here is an interesting one. So we have an array 3, 7, 4, and we say, okay, I is an integer, and I compute as indexed by I plus 1. What should this be? Well, if I is 0, 1, or 2, that's fine. So we should get those 3. And all the other values of I, you can imagine, means that it fails. So we won't get those. So this will compute to whatever it is, 4, 8, and 5. And so this is usually called narrowing in logical programming. And it's also a cool feature. You can sort of, you don't have to explicitly index things. You can just say, oh yeah, I have this thing, index variable, and that index variable will automatically range over the domain. So what are these arrays and tuples? Well, so to a very good approximation, they are just functions. They are functions from the numbers 0, 1, 2, and up to n minus 1 if there are n elements. So when you write a square brackets I, that is really a function call. I'm calling the function a, which is the array. I mean, it could be a function, but say that a is an array, and you get the ith element. And if you write it with square brackets, it means that yes, this is a function application that is allowed to fail. If you write it with round parentheses, it means no, this application must not fail. And it is the work of the type checker, or verifier as it's called for verse, to prove that if you use round parentheses, it will not fail. So in this example here, the first one, so if I index a with 5, and then I can print x if it's there, otherwise I do something else, that's fine. No real proof obligation here. But if I say print a round parentheses 5, it means that the compiler will have to work harder. And if it can't prove that 5 is in the domain of a, then you will get an error at compile time. So Verification is super undecidable, but we don't care. We'll do a best effort. Okay, so now we get to types. Yeah, I have 1 minute to talk about types. So what are types? Well, let me skip ahead a little bit. Types are just ordinary functions. And the function succeeds and returns the input if you're in that type. So a type inverse can be any collection of values. It doesn't have to be something like int. You can make a type of prime numbers or a type that has 5 and the string hello in it. I mean, these are valid types because it's just a function that says, yes, it's in there or it's not. So it fails if it's outside the domain and succeeds if it's inside the domain. And you can write your own types that have your own predicates. So of course, this is very undecidable. So let's just go through a small exercise here. We had arrays. Can we make a type of arrays? Well, array of T, that should be the type of arrays where the elements have type T. So there is a type called type, which is the type of partial identity functions. Okay, so what should this look like? Well, I mean, it should then accept an array, and it should test that all the elements have the type T. And how do we do that? Well, you could say for A in the array, we want to test T of A. Cool. And this function, it looks a bit familiar. What if we make it slightly more general and say that, oh, it doesn't have to be a type, this thing T. T could be any function from A to B, which also includes types. Look, it's the map function now. It takes something from A to B, an array, and it loops over the array and returns the new array where you've applied that function. So it means that this array thing is a proper functor. It works both on the type level and the value level. I see that Eric is smiling. So I promised you at least to show you what this x:t really means. So if you write x:t, it really means there exists an x and an I such that x is equal to t applied to I. So when I write x:int and x is equal to 3, I am really saying, well, do there exist x and I such that x is equal to int of I and x is also equal to 3? And yes, we can solve that. If I is equal to 3 and x is equal to 3, then that works out. But if x is equal to foo, no, there is no I that I can pick. So that thing would fail. Failing is not necessarily a bad thing. If you're in a position where you're allowed to fail, like in the condition of an if, that would be perfectly acceptable. If you're in somewhere where you're not allowed to fail, then the compiler would complain and say, no, sorry, you're not allowed to fail here. Yeah.
I'm just wondering if that implies that you have one representation of numbers. So can you have a 3 which is an integer and a 3 which is a floating point number?
They have little different suffixes to distinguish between floating point numbers, and so they're really rational numbers, the ones that are written as 3. You have to write 3f for a floating point number. I mean, I don't think it's great, but yeah.
Does that mean the predicate for a type needs to be able to operate on numbers independent of the representation?
I mean, in the worst case, yes, but you'd hope that almost all these type tests will be resolved at compile time. Yeah, I think I need to leave the last couple of minutes. Oh, I should just say that there is a version of Verse if you download Fortnite or rather UEFN, Unreal Editor for Fortnite. You can run programs, and you can run your little code, and then you say start it, and you will drop out of the sky, and you will fall down to the ground, and you can walk up to a monitor, and you can read the result of your program. So that is a version of Verse that does not have all these fantastic features, but there are people programming in it. There are hundreds of thousands of these things called islands that you can make with this. I don't know, do we know how many people are programming in Verse? Thousands. Yeah. And if you make these islands, and anyone can use them, if they become popular, you make money. And there are people who live on making these islands and programming in Verse. So it's not entirely theoretical. Okay.
So we also have the JS panel after that, after this. So if you could come up if you're part of the panel, and we'll do questions with Lenore now.
Does it have a module system?
Yes.
And I guess you alluded to the fact that it bridges with C++, so it also has a story to go either way, I guess? Or?
Yes, I mean, I don't know how much of that is working, but yes, I mean, it's supposed to go both ways.
So you mentioned a couple of times that, like, you know, the billionaire kept, like, you know, pays, and then you just kept, like, implement what they ask for. I've seen that at Microsoft, where Bill Gates was the product manager, and at Facebook, where Mark is the product manager. But maybe sometimes people should just push back, because, I don't know, like, you get maybe weird things if you just do what, you know, the person that pays got, like, wants.
It's pretty easy to push back with Tim if you have sort of a technical argument, and you can say, okay, this is not sound. But if I say, I don't like the word false for this, then Tim will just say, I like the word false.
But I just want to add here, how often are you with the CEO of a company and you say, I don't understand this? Just look at just think of the denotational semantics.
Yes, that's what Tim usually says.
This is our weekly call.
Yes. Tim is a really, really smart guy, and he knows a lot about languages and semantics and so on.
Is the negation of a type also a type? Type is a partial function. Can
yes,
I say not?
I guess that it must be. I mean, all the elements that are not in a type, yes. Can we express that? Yeah. Yeah, I think you can, yes.
Can types have mutable variables?
No, types are sets of values, so they don't mutate.
Okay, so every time I look at Verse, I feel like there should be a connection between choice and parallelism. Is that like intuition correct, or am I just misled?
No, not fair.
I mean, I'm sure there are some situations where you could use parallelism. If you have a for loop with a bunch of choices, you could do them in parallel, but that's not sort of the intention.
Currently, Unreal is single-threaded, so anyway.
Is any top or dynamic or for all?
I wish I knew. I'd say it's top.
Yeah, you said that types are sets, so what about types like x equals x arrow x?
Yeah. That's a good question.
Thanks for asking.
Are you unemployed? Do you need a job?
Any other questions? Okay, let's thank the speaker again. So we will start the JS panel in about 2 minutes.
Hello, I'm Matthew Cadet. I work at Mozilla on Firefox and specifically the SpiderMonkey JavaScript engine. I have been doing Firefox for 7 years. Before that, I worked on an ill-fated Ruby JIT, a Java JIT, and then before that, a C and C++ compiler. So I've been doing compilers and runtimes for a long time. Oh, and I did my master's on transactional memory. So that's why I'll never work on Verse.
I'm Sam. I work at Epic Games leading a team working on the Verse VM Leonard was just talking to us about, and leading a team building a new VM for Verse and transactional memory compiler that auto-transactionalizes memory for C++ code. Before that, I was working on JavaScript core for 8 years. I guess I'll just preface that I'm not speaking on behalf of the JavaScript core project here, just my experience working on it before joining Epic.
I'm Shu. I'm Shu. I work on the V8 project at Google. This is the JavaScript engine inside Chrome. Been there about, I guess, 5.5 years. Before that, I was also at Mozilla. I was working on SpiderMonkey, doing the same thing, different engine. So I have some history with JavaScript at this point. Mostly I work on the language evolution side, standardization, new features, less of a hardcore compiler engineer these days, mainly do feature implementation and stuff like that, and arguing with people in the standards committee.
Thank you. So I am Manuel. I'm a pure academic. I'm working at INRIA in France. And for about 10 years, I've been working on the implementation of the Scheme programming language. And at the beginning of mid-2025, something like that, I switched to web programming and I created the system Hop, which is a multi-tier programming based on schemes. That is, it's a particular system where you write just a single program and you put annotation. And with this annotation, compilers go through and decide which part is going to be executed on the server and which part is going to be executed on the client. And all that was implemented in pure Scheme. So Scheme for the server was compiled to native code, and for the client, it was compiled to JavaScript. And I don't remember exactly when, but about maybe 2010, something like that, I met Mark Miller that convinced me to rebuild this system hop for JavaScript. So I did the other way around. I have built Up.js, which is exactly the same system. That is, you write just a single program, you put annotation, and some part are for the client, some part are for the server. And now the game is different because actually with Up.js, what I do is I compile JavaScript to Scheme for the server. So now I have compiler from Scheme to JavaScript and JavaScript to Scheme. And this conduct me to study the head of time compilation of JavaScript to Scheme. So in this panel, we are going to talk about a general problem of implementation of JavaScript and maybe the future of implementation of JavaScript. But as we assume that you are not so familiar with head of time compilation of JavaScript, and in particular what I'm doing in Hop, we will begin this panel by me giving a brief presentation, which is just a small part of a presentation I gave at ICFP about the head of time compilation of JavaScript. So I will start by that, and then we have a bunch of topics, bunch of questions, and maybe we will interact with you if you do have some specific question. So I will give this, I guess it will last something like 10 minutes, or I will try to make it last no longer than 10 minutes. Okay, good. So compilation of JavaScript. So I guess that in the room, you are already familiar to the implementation of JavaScript, but still, for those that are not exactly so fluent in JavaScript, I will just start with a couple of minutes explaining the main problem of compiling this crazy language. So let's have a look at this statement, and let's assume for a while that we are C developer or even Java developer. How would you compile these things? It's pretty straightforward, pretty obvious. This is exactly what we teach to our students almost during the first year. A loop of this kind, you just compile it to assembly code, and that's fine. You know what it is, you have your register, you can have the increment, the comparison, all that is absolutely trivial. It doesn't take to be so smart to generate this kind of code. Good. So now let's pretend that we are JavaScript developer. Let's pretend that you are JavaScript developer. Well, what is the meaning of these things and how should we compile it? Well, it depends, because if A happens to be an array, probably you could expect that you will generate the same code as the one you have generated for the C code. This is what you can expect from a compiler. Well, yes, but A might be something different. For instance, A might be an object of this kind, where it has a property named length, it has a property named 0, it has another one named 2, and you can notice here that I have paid attention not to use the correct order 0, 1, 2, but 0, 2, 1, so that when you will iterate over that object, you cannot expect to just be walking through a linear memory chunk. So if A is of this kind, that is, it's not an array, you can imagine that the compiler is facing another situation and it should probably be generating a different code. But A might be something else. It might be an array where you remove one element, and so when you iterate over it, when you hit the array number 1, then you have to go through the prototype of the object. So it's not that you are just walking through your memory, but you have to jump through a graph of pointers. And situation can even be worse, because you can have something like that if I is no longer an integer but a string. You are just concatenating things on the strings and just accessing the object itself. So you see, just compiling this stupid loop is just a nightmare. So the question and the problem is that the structure of the language does not help the compiler as it should be or as it does with another programming language. And this is, from my point of view, the main difficulty we are facing when we are trying to compile this language ahead of time. That is when you don't know the actual shape of the value you are manipulating. So does it make sense to try to compile JavaScript ahead of time? Or maybe yes, it does, because in some situation you are forced to use ahead of time compilation. And typically, if you are using a platform where you are not allowed to generate code at runtime,
This is one of the situations where you need to have the time compiler. But also, if you have a very limited machine with very restricted memory, for instance, you cannot afford to embed your compiler in your executable, so you need to compile ahead of time. But it may be also other situation where it makes sense. For instance, if you have very short-living executions, maybe if you have a JIT, the JIT won't have even the time to compile before the execution is over. And in the long term, if you want to save some energy, for instance, for executing your application, then it would be better if your application is compiled once for all. And also, to be totally honest, because from an academic point of view, it's really an intriguing question. Is it possible to get good performance by compiling JavaScript ahead of time? And maybe this was my main motivation. I have a better understanding of what is the situation of a language such as JavaScript. So how to attack the problem? It seems to be a crazy story, a crazy idea. What could we do? Well, we do everything we can. So a little bit of typing, a little bit of data flow analysis, a little bit of control flow analysis, and a lot of optimistic heuristic. And I will present 2 examples of this kind of things we are doing. So optimistic compilations, pretty straightforward, the idea. Consider this definition of Fibonacci. What do we do in practice? What does up do in practice? Well, it generates 2 versions and a dispatch. So when we compile fib, we compile actually this version where we discriminate on the type of the arguments, and we have 2 specialized versions for Fibonacci. Pretty straightforward. What is the real benefit here? The benefit is in the function which is dealing with integer, we are able to use specific operator and not the generic one. So this is where the improvement is coming from. So maybe you may ask the question, okay, that's very nice, this setting, and that's pretty straightforward. You can imagine these things by yourself. But the real question is, how do we decide here that we want to generate a version for integer? That's the main question. And this question has been considered difficult because in some sense, you may have the impression that it requires a very smart type analysis for detecting that, yes, you may be generating a version for integer. Or either a type analysis or maybe an abstract interpretation for detecting these sort of things. Well, something really complicated in terms of compiler. But absolutely not. This is not what we do in UP. We do something absolutely straightforward, absolutely silly, but that works extremely well. And what we do is the following. Instead of trying to infer the type of the Fibonacci function, we just try to find the type for which the compiler will be able to generate the best code. And that's the type of the variable we decide. And this is extremely easy to compute these things. You just need some syntactic rules that you apply sequentially. It's a linear algorithm. And at the end of the algorithm, you have a type. And you say, OK, this is the time for which I generate a specialized version. It is extremely easy to generate. And consider something like a super sophisticated type analysis that will give you a very precise type for the function. Maybe it will generate a type, which is correct, maybe not. But maybe it will be a type so precise that the compiler will not be able to use it for improving the code it generates. So you don't really need something very specific. You just need something that is useful for the compiler. And so this stupid idea let us generate very efficient code for JavaScript. Okay, so the idea is that all that is implemented in this system called UP.js. It is available. It is an open source software. It supports full-fledged JavaScript. It's almost compliant with this version of JavaScript. And it also supports all the Node.js runtime system. And it has some unoptimized features, and in particular, it does not optimize so far floating point numbers, just because I've not been interested in this particular aspect and because I have to make some sacrifice because I have just one life, actually, to live. So, JavaScript. The other problem is that JavaScript is a huge language. So how do we, once again, attack the problem for being able to implement it completely and efficiently? The solution I have adopted, as I have presented earlier, is to generate JavaScript to scheme. And then I reuse my scheme to C compiler, and then I reuse GCC for generating an object file. So a very, very overview of the differences between Scheme and JavaScript. So I don't know if you are familiar with Scheme. I don't expect you to be familiar, so bear with me with just this slide. I'm defining a function, and just after that, I will re-implement the same thing in JavaScript so you can notice the difference in between the two languages. So I'm defining a function that generates itself another function. In that one, maybe I can use this. In this function, I have two free variables, c and t and base. This one is an integer, this one is a floating point number. And here I increment this c and t variable, and I return this constructor. Pretty straightforward, regular Scheme code. How do we compile this thing? Well, we compile it as this function will be a closure, which is there. A closure point to some piece of code, some assembly code that is generated by the compiler. This closure has two free variables, CNT and base, and you see them here. CNT is put in a box because it is mutated, and when a variable is free on a closure and it is mutated, it has to be put in a box because this is a decision of the Scheme compiler. And this one is a floating point number, and it is allocated because floating point numbers here are allocated because of polymorphism. Okay, so now the same function in JavaScript, exactly the same meaning. I have my function over there. Here, the two free variables, it's just a difference of syntax, but it's exactly the same. How do we implement this thing? Well, we start with the Scheme closure, but on top of the Scheme closure, when we are compiling, we have to add some extra stuff for JavaScript. And what are the extra stuff we have to add? These ones. So now you have an idea of why JavaScript is not so efficient, and the difference in between JavaScript and a normal functional programming language. But still, because we are using Scheme, and because we are using this idea of heuristic and optimistic compilation, most of the time, we can avoid generating this crazy closure for JavaScript. How do we do that? Imagine this piece of code. We are just using the library function for each. The problem with JavaScript is that you don't know if this variable over there is really an array, and you don't know if this variable has overridden for each, so you don't know if you are really invoking the library function. But you can make the assumption that very likely it is. And in the fact, for all normal program, it is. So you can compile that, assuming that you will really be invoking for each. So how do we compile it? Well, we generate the Scheme code that just create a Scheme closure, not a full-fledged JavaScript closure. And we invoke this function here. And we create a Scheme closure, which is even allocated on the stack, not on the heap. Sorry. And then the purpose of this function is just to check that this variable over there is not overriding for each. And if it is not, then we get the same performance as the Scheme compilation. And if it is overriding it, then we go to a slow path and we will do the real things. And you see, this is another example of optimistic compilation. We assume that the programmer knows what he is doing, and we generate code for programmers that indeed have an idea of what a real program should be. Okay, so just in conclusion, the benchmark, to get an idea of the performance we get out of all that. So for the benchmark, I'm not using the standard ones. I'm not using Jetstream, or I'm not using Octane. I'm using a different way of benchmarking things. What I did for this thing is I reuse programs that I know to be used. And for instance, this one here, it's a JS of OCaml, so the implementation of Camel on the web that is used by companies. Or what I use is NPM packages that have no dependencies and that have an extensive test suite. And I take this test suite and I make a benchmark out of it. So by doing so, I'm sure that I'm using benchmarks that correspond to something that is used widely on the web. And for this graph here, instead of just generating one executable and one execution, I take the benchmark and I increase the complexity of the input. So when the complexity increases, the execution time also increases. So now I have a notion of how the program behaves when the input is more complex. So on this graph, you see up V8, SpiderMonkey, and JavaScript core. So let's zoom on just 4 of them. BAG is just a simple numerical program. BASIC is just a basic interpreter. This one is a scheme interpreter, and this one is a markdown parser. So you see that up, sometimes is faster, sometimes is slower, but it's not ridiculously slow when compared to the other system. And for even some benchmark, it's performed really well. Generally speaking, what I have observed is that Hop is something like in between 1 and twice slower than V8, something like that. And so on this benchmark, you see that Hop is not as good as for the first 4 ones. This one, I don't remember what it is implementing. Minimist, I think it's a magnifier for JavaScript. This one is the most popular NPM package. It's a library of time. And Hop is not performing so well because Moment is allocating a lot of objects, and the Hop compiler is generating C code that is using the BUM collector, which is a non-moving collector. And so here, this is not an ideal situation for a non-moving collector. This one, I'm very proud of it. Hop is the fastest implementation when you are dealing with proxies. And this is because we are playing a nice trick for implementing inline caches with proxies. And if you are curious about that, you can have question why Hop is outperforming everyone regarding proxies. Okay, so I think I will end here. I hope you are kind of convinced that it's not such a silly idea to try to compile JavaScript ahead of time. And if you rely on heuristic or new way of compiling, yes, you can get decent performance and probably performance that are comparable to the other implementation. And I know this is not a scientific argument, but if you compare the size of the team developing V8 or JavaScript core and just myself, you may have an idea that, okay, if maybe we were 10 working on Hop-C, maybe we could have really competitive performance. No evidence of that, but still, this is an intuition. So this was just a very brief overview. So you have an idea of what Hop is and in which direction it is going, how it compares to the other systems. So it will be useful for engaging the discussion we will have now. Thank you.
Yeah, we're happy to take questions at any time.
Yeah, so maybe we can alternate question we have prepared and question we may have in the room. So maybe the first thing we could discuss is, according to you, according to the 4 of us, what is the main source of inefficiency of JavaScript? What is the most impactful property, or what is the most painful things that we have to implement when implementing JavaScript? I have an idea, but the impact in terms of performance, the one that is the most expensive, the one that makes JavaScript not so fast. Well, could you develop on that?
I mean, what you were talking about with something might exist on the prototype chain, you don't know the layout of objects. Property inline caching takes essentially, like, gives you large constant factor optimization over what you get if you have like traditional lookup in a naive way where you're looking up something in a hash table. So you turn a hash table lookup into like a branch in a load or a constant value potentially.
I mean, I would say at a higher level, I would say the thing that makes JavaScript slow is a lack of attention to making a fast language when it was designed. Like, it was evolved. It grew in, fits, spurts, and jumps, and it doesn't really lend itself to being fast naturally.
I think the fact that it is as fast as it is in production runtimes is a testament to like the amazing work that has happened over the course of the last like 30 years, 40 years, you know, all the way back to Smalltalk implementations. There's techniques that we still deploy every day. So it's just not a great language for going fast.
Do I talk into this? Okay. Yeah, it's just a very dynamic language. So it's just like if you write JS like C, I'm pretty sure all the VMs will be pretty good. Like Asm.js was basically kind of like that. But if you write JS as the world writes JS, you will hit corners. We optimize where we can. We even try to remove some of the dynamism by doing backwards breaking changes. The biggest one was eval, right? So if you don't know, JS lets you dynamically evaluate code as a string. And this is crazy enough that like you are able to introduce new bindings into the into the scope of the place where you called eval. This, as you can imagine, means that you can't even compile like a good representation of your local bindings into your stack frame. So we changed eval to only be able to do that if you call it with the string eval. So if you, because otherwise you would have to do full like interprocedural analysis to see if any function call might actually be evaluating dynamic code. So that was intractable to analyze. So we changed this part. So at least if you don't use eval, that you have basically static scoping, static lexical scoping that we can use to compile better. But otherwise, yeah, it's the stuff you said. It's the index properties on prototypes, recal especially. So like, don't ever do that. If you do that on a web page, that makes you fall to the slow path, and everything will become slow for like the duration of the page. We continue to make recent mistakes, in my opinion. Like I said before, I'm mainly involved in future features in language evolution, and I think some of the recent features, we erred too much on making them nice to program into type, and they're just really hard to be fast. Like, for example, iteration. If you for of something in JS, which is kind of like the iteration as you expect, that allocates a result object every iteration. That's not great if you want things to go fast, and this is hard to optimize. It's hard to optimize without sufficient type feedback and stuff like that. So, yeah, the language just sucks.
So I have a question. So I was on the VE team when ES6 became a thing, and it was a major overhaul to the VM, and it was disruptive. Let's say we basically had an entire sub-team. So actually, maybe you kind of touched on that a little bit. What is the feedback process for TC39 for those features? Because back then, VM implementers had a lot of power.
I think so TC39 works in practice by a single veto system where any delegate can technically just say no to a proposal and prevent it from moving forward. And we now, after ES6, ES6 was at this time when, like you say, this whole bag of features just dropped on implementers. And that was a bad time. And since then, now there's a more granular feature proposal that goes through several stages. And there's a particular stage at number 3 that says it's time for people to try to implement it. And if you are an implementer and you have trouble implementing it for whatever reason, like you can't make it fast, you should come back and request redesign at that time. So the feedback loop exists. It doesn't always work great because the VMs have somewhat converging architectures, but we have made different choices. And so because things are prioritized across different teams differently, if V8 implements something later or earlier than others, and we give feedback or we don't give feedback, it might be fine for us, but it might not be fine for SpiderMonkey, it might not be fine for JSC, and then we might discover it too late because Chrome decided to ship first, and now it's on the web, and now we have to take extra pains to unship it if we try to redesign it. But in short, feedback loop exists, still definitely could be improved. And it's also a point of contention for like, oh, if we make this feature more static because it's better to compile, there's another contingent on the other side that says that will make it harder to use. And we want it to be nicer and easier to use, and you have to argue with them about it. But, oh, another thing you said, do the VMs still have a lot of power? I believe the VMs still have a lot of power as gatekeepers, if nothing else, because we're the ones kind of looking out for performance over pure usability.
I have a follow-up question to that. So it's about ES 2015. One thing that I noticed from just like a user perspective is that among the large number of new features that dropped, there were a lot of features that were individually great, and it would be great if you could use them together, but they didn't go that well together. So for example, you had the introduction of const, which let you do lexically scoped immutable assignment. You had destructuring assignment, and then you also had the async await syntax that let you do, I guess that was technically 2018, but that let you do try catch. And because if you want to do something like call an asynchronous function, it gives you a response in a promise that has an object with fields. And ideally, we would like to destructure that into a variable, but you can't if it's in like a try, right? You'd have to do let outside of it, and then assign it inside the try. But the point being just that I feel like there were a lot, from a user perspective, it felt like a lot of the features were really difficult to use together. And I'm curious if that was also the case from a like compilation perspective, if it was difficult to compile combinations of those things more so than you might expect as a baseline.
I've spoken a lot. I wouldn't mind if someone else took this.
I wasn't around for most of this. But one thing I would say is that this is a flaw of the JavaScript evolution process, is that a lot of things are developed not with compatibility with each other in mind. And we run into this thing all the time. And, you know, we get into situations sometimes where we've shipped syntax and it's kind of like, ooh, that actually kind of doesn't work out that great. And this comes back to the question of that feedback loop and how do we do it? How do we get better feedback earlier before things hit the web? Because one of the takeaways that I'd like people to come away from this is JavaScript is this weird language because there is only one version of JavaScript in the grand scheme of things. There is the JavaScript on the web. And it is, to a first approximation, almost impossible to undo mistakes. We have from Mozilla, we have two things in flight where we're like, we would like to undo some mistakes. And it's hard. And, you know, we're kind of hooped on this. But what this means is that like the JavaScript evolution has been kind of awkward because things look good in independence. But it's when you consider the cross product of all of the features of JavaScript that then you start to get into trouble. And it's not just implementation. It is also just like usability of the language like you talk about.
One thing, we keep blaming on JavaScript, but on the other hand, we have to admit that JavaScript is one of the unique language where you have several implementations that are so compatible. And this is an achievement. So maybe, I don't know, the evolution is not that great, but still we have compatibility, which is amazing.
Yeah, no, and like I would say that the dedication to backwards compatibility is phenomenal. Because realistically, like the goal here is that anybody who authored a web page in 1998, awesome GeoCities page, it should still run and it should still look and work the same way. And there are times where we have broken backwards compatibility, but it's rare, infrequent, and ideally with as low impact as it can be possibly made. But we have to defend this with a lot of rigor. And sometimes what falls out of this is like, I think the TC39 process is really good at doing the individual pieces. But what TC39 in general lacks is like, there's no dictator. There's no somebody who sits there and is, the Tim, I can't remember his last name, Sweeney, thank you. There's no Tim Sweeney at the top sitting there being like, my taste dictates that it is false, right? And design by committee works a lot better than you would expect, but it is still design by committee.
Let's see if I form this in a way of a question without trying to give my opinion, but it does seem like, people know the evolution of JavaScript started as a scripting language, just kind of make some things jazzy on a web page. But now people ship, like building real products, writing millions of lines of code in JavaScript. And there's a move, I wonder if it's your take on, it's kind of being bifurcated between the people that do a lot of tooling, like there's a lot of build steps in tooling, and then I think a lot of the things that, if I'm reading what you guys are saying, right, that kind of like dynamic change string to where you break the prototype chain and all that. So I wonder if there's like different users that are forming and in this big move towards not ahead of time compilation, but like ahead of time tooling. There's a lot of like build. So hopefully my opinion makes sense. You can take it whichever way you want.
So your intuition is correct. I'm pretty sure that there is a pretty big divide between the folks who use ahead of time tooling, like transpilers, TypeScript. TypeScript is rocketed to popularity. Everybody who's like a serious web developer uses TypeScript. And we have survey data, and I don't know, I think Google used some statistics thing. Like we estimate most of the money generating web uses, like the people who develop for that part of the web uses some kind of tools. The hobbyist folks still exist, of course, but they have kind of drifted farther and farther away from each other. If you optimize a language for business, that's very different than optimizing a language for fast prototyping, for all that kind of stuff. And where the money is and where the investment is optimizing it for business. So I think that leads to a lot of friction and feeling hurt in the community of a lot of the investment is away from the hobbyist people who grew up with the old web, being able to view source. It's not minified. I can just write something, load it up, send it to my friends. It all works. That's a nice dream, but it's gone, I think. By and large, it exists in small bits, but I think the future evolution of the language is that there's enough industry in it now that we need to push it to be more like a grown-up, I don't want to say that strong a value judgment, but we push it to be more amenable to the needs that to be more demand-driven for what people are using it to build today. And people are building sophisticated stuff, and they are used to tools and sophisticated stuff from their other tool chains, their other stacks that don't exist, and that need is being filled. And yeah, I think the language will further go that direction.
I have a slight counterpoint, which is that I agree everything about the professionalization, all that sort of thing. I think it's absolutely worth defending the old web, the view source web. I think that's a beautiful thing that we should absolutely be trying, because there is a generation of people, like I have a little kid. I have no idea how she will ever learn how to do anything on a computer, because her experience of computers is so wildly different than mine. And I just don't understand how it's going to be. And like the view source web was kind of part of that, was this ability to see how systems are made. And we don't have that anymore. The thing that I would say is that JavaScript is this crazy world where everything changes and turns over every 5 years, where frameworks live, die, you get new framework, you get new tooling. TypeScript's amazing right now. Who knows? 10 years from now, maybe TypeScript will be the C++, it'll be the Spring Boot of JavaScript land. And I actually kind of would love to encourage that more, where I love the vibrancy of the JavaScript ecosystem, and I want to see more people building interesting experiments and having them grow. And I think the professionalization of JavaScript is actually kind of a problem, because it cuts off a lot of these projects at the knees. If you wanted to come out and you had a cool, you come to Splash, you see a cool type checking paper, and you're like, wow, I could build a type system like that for JavaScript, and you want to build it. It's a lot harder to motivate yourself these days when you're like, and no one will use it because everyone just already uses TypeScript, right? And I kind of think that's a little sad.
So for each of you as language implementers, what do you think has been the biggest source of wasted time and effort for you when it comes to speeding up JavaScript execution?
As in not being successful?
Yeah, your white whale, or something that you thought would pay off and it just kept not, and it totally wasn't worth it in the end.
I will start, so you will have a couple of minutes to think about it. For me, the most painful things are the lack of fixed number arithmetic. The fact that you only have floating point numbers, and the fact that you have to detect the overflow, so you go through a floating point, etc., etc. This is a really painful thing. The extensive API for strings and for regular expression is also something very complex. And also the complexity of arrays. The fact that you don't have just a stupid vector where you pre-allocate something and it is there forever. The fact that the array can grow or shrink, or you can delete elements of an array, for me this is just a nonsense, because this is combining something like list and vectors in just one single data structure, and this is really difficult to get this very efficient. So for me, one way of improving JavaScript might be to just add a new data type that would be vectors, for which you could not remove elements and that you could not extend or shrink.
I've implemented a lot of things in JavaScript core that we threw away. I don't think I would view it as a waste. I think you learn a lot from things that end up not being faster. Most of the experiments we did that didn't work out are trying to find the balance on the latency versus throughput trade-off. So I wrote a lower tier optimizing compiler, ended up not being worth the throughput gain given the latency introduced in having to OSR exit back to the cost of tiering up through your various tiers just wasn't worth it. I also experimented with a tracing compiler for a baseline JIT, was also not worth it. Baseline JITs compile fast enough. So I think those were, in a sense, thrown away work, but they're not wasted just because the project gets to learn about what works and what doesn't work. That's how you make progress. Every JS engine team, I'm sure, implements 10 things, and you might only ship 8 of them or 6 of them, depending on things getting faster or not getting faster. For all of the speed ups you see, there's a bunch of work that these teams are throwing away because they just didn't work.
I would frame my answer very slightly differently, which is that I've mostly thrown away other people's code. And what we have, kind of a learning of our team over the past while, let's say the past 5+ years, has been one of the biggest dangers is being overly obsessed with performance at the cost of complexity. Complexity is a real pain, and some of the stuff that I've thrown away was good for performance, but it was good for performance in very narrow circumstances. And throwing away that stuff throws away all of the complexity associated with you. And then you take a performance hit and you go, I am at peace with this because I now have a much less complex code base. My favorite one being the code I threw away, and then we immediately got a CVE on it, and it was already writing the train to beta. So we didn't have to do anything other than just uplift the patch that deleted all the code. But this is a danger.
The biggest failure I remember is probably tracing. So as a cautionary tale, don't do tracing for JavaScript, for web workloads. So this was not at Google, this was when I was at Mozilla. The first JIT compiler in Firefox was a tracing-based JIT. And if you read the tracing paper, it's like catnip. It's wow, this thing is great. Why wouldn't we do this? And then it turns out that for web workloads, and Mozilla spent multiple years with teams of 5+ engineers learning this, you overfit on all the workloads. And first of all, web workloads live very short. And tracing is just uniquely badly positioned to do that. So if your workloads never reach kind of type stability, you never get this like core fast loop that gets traced and optimized to shit, you end up having many small traces you have to try to reconcile. You're trying to go back to like a method at a time compilation world badly because all you have are execution traces, and you have so much complexity that need to like go back to the generic case. Anyway, Firefox shipped it and then learned the hard lesson that it's great for, you know, long-lived physics core things, physics simulators, and then later ripped it out.
Okay, here's a question. I've read a book called JavaScript, The Good Parts by Douglas Crockford many years ago. He described a simpler subset of JavaScript, for example, without eval and with stricter scoping rules. But that was many, many years ago. And I think even before the introduction of let and const in JavaScript. So I want to ask, does anyone make any attempts to create a better subset of the language, or will it happen in the near future? Thanks.
I mean, I guess I have to ask, what do you mean by, like, how do you envision this better subset to be used? Are you envisioning JavaScript removing features, or are you envisioning some subset that gets popular in the ecosystem and people agree that we should avoid some of the features, but they're still there? No, that's never going to happen, because we can't break the web. Websites that were written in like 96 and are not updated but are still there must remain working. Yeah, but how do you do that without breaking stuff? The problem is not for code that is still being updated. The problem is code that is not updated and maintained must remain working. The problem you're trying to solve is not how to update code that is still maintained. You can break those because they're still being maintained.
Sorry, I forget when, but I think at one point JavaScript introduced the use strict. So maybe there's a use static type strict. I don't know. I'm just making.
You can introduce a third thing.
I'm just trying to.
But to jump on this thing, if I may, Google has tried strong mode.
Oh yeah, that failed.
Yeah. But I think this is the answer to your question. Google has tried to introduce this stricter thing than use strict, which was use strong, and it has failed. And I don't remember exactly why it has failed, but I think that because it has not reached the level of performance it was expecting to reach, so it was not worth maintaining this thing, if my recollection is correct.
So
maybe
I can answer the strong mode. So strong mode was a brainchild of Andreas, and it didn't really work. It was very disruptive to V8. Literally everything was touched by strong mode. And so it was a cross-cutting change to the VM. It didn't really seem to make anything faster. There was no code that was written in strong mode. It had to be so strict that you could not do anything. So like all the things that people do in JavaScript, it was really cutting it down to the bone. It was basically a completely different programming language. So it didn't really work out because of a lot of reasons.
So I have this dumb idea that I keep kicking around, not seriously enough to actually do anything about it, but to your exact idea, which is this one where a lot of the features that I dislike, you can sort of identify textually. So like symbol.unscopables or like toString tag, or there's a whole bunch of like weird symbol things where to support this one thing, we want to make sure that somebody can opt out of it for this other thing. And I've thought about, in the year of our Lord 2024, we could just compile like SpiderMonkey as it is today to a WASM file, put it in Firefox. Whenever we see bad code, old code, we just boot that up, we run it in there, And then in modern SpiderMonkey, we rip all that code out. We just delete it. And then we just statically tell ahead of time, we're just like, oh, this is old JavaScript. Go over here, be slow, it's fine. Now, it's a dumb idea, like, on its face, but I keep kicking it around because I would love to. I have very similar feelings to you. It's like, couldn't we get rid of this? And no.
Hello. So this question has a couple assumptions that if they're wrong, I just want to be corrected on them because I want to understand more from your expertise. So my very vague model of performance is that the things that make programs slow are, one, having things that the compiler can't predict so you can't inline and then do optimizations on the inlined code, and two, having a lot of like memory allocations or deallocations. So I know there's like speculative inlining work being done for various JavaScript VMs. That addresses the first one. For the second one, there are some garbage collected languages like D or Go or like Ben's language Virgil that have interior pointers, and this seems like a way to reduce the absolute number of allocations while still having like objects inside of other objects. Is this at all something is like kind of a performance, like contributes to the performance ceiling for JavaScript, or is it just like not really that important and there are like many other things that like matter a lot more for performance?
Yeah, but I mean, if you have interior pointers, now you've lit your JavaScript or garbage collector performance on fire, because now tracing's way more complicated. So I don't know if that trade-off would pay out the way you think it might. You know, I think you're right generally about the high level. What are the things that make things slow? There's a lot of extremely clever techniques inside of VM engines in order to try to cover this up, and I think, coming back to my point, JavaScript is remarkably fast for how bad a language it is for making it fast.
Some other element of response to your question. With my setting, I'm in a good position to evaluate the slowliness of JavaScript because I'm able to compare to Scheme. And Scheme somehow behaves as JavaScript. It's a functional programming language, but you have side effects and you keep allocating a lot of objects, and et cetera, et cetera. And when I'm compiling JavaScript to Scheme, I'm in the end using exactly the same runtime system for JavaScript and Scheme. And what I observe, and recently we have had to run some benchmark comparing the performance of JavaScript and Scheme, is that on the top of my head, JavaScript is about 10 times slower than Scheme. So the problem is not coming from the garbage collector. The problem is coming from all this extra infrastructure you have to allocate for any object in JavaScript. And in particular, the fact that you can add property to any random value in JavaScript, it's just a nightmare. Just look at the closure. In Scheme, a closure is just a pointer to a function and an environment. In JavaScript, you have to be providing fields for the inline caching, the hidden classes, and also all these things. And this costs a lot. So objects in JavaScript are just fat. It's not that you are allocating them a lot, it's that they are fat. With my implementation, which is the same runtime system. So it's kind of a fair comparison. It's in between 5x and 10x.
Okay, I have a two-part one. I don't know if we have time. The first one is, where will we be in 5 years? And the second one is, what would be like something radical that we could do?
So I think in 5 years, JavaScript will look pretty similar to what it looks like today. Like it's an evolving language. It's not going to radically change. It's going to stay largely the same. One thing I would say is I would love to see academia pay more attention to JavaScript. What are things that could be done in the language? What are ways to improve the language design? Some holistic investigations into the cross-product problem, like how do we be better about designing language features so that we know that they're going to work together. And there are some groups who are doing really great work with JavaScript. There's a group at KAIST who's doing extraction of static semantics out of the the JavaScript spec is written in text, and they extract machine-readable versions of the semantics so that they can do model checking, proofs, and type checking on the actual spec. It's great stuff. But I'd love to see more. I think academia is great. One interesting note, we recently got on very large, stupidly large WASM modules. We just got a 75x speed up in compilation time, and the answer was stop computing your dominators like it's 1980. But this is the kind of thing where I also think academia can help. Is come up with new algorithms that are better, that have better runtime. We fixed our SSA construction, dominator construction. We got 75x. There are other interesting things out there. Things that are slow. There are things that we could make the language faster. And I'd love to see more work there.
And I think the biggest thing, so one thing that we haven't really talked about, but all the production JS VMs and browsers have is that they run both WASM and JavaScript. And WASM is evolving in a different body, and it's adding new capabilities. And one of the things that I've been trying to do, and the WASM folks have now trying to do, is to add shared memory multithreading to JS and WASM as one of the last frontiers of things you literally cannot do on the web. So once we do that, if we do that, I shouldn't be so confident, because there are people who are against it in principle, and it's just very hard. And the reason it's hard is that the engine and the garbage collection systems have been built for the past decade on a heavy single-threaded assumption. The GCs themselves might be concurrent, but the mutator is certainly not concurrent. What happens when the mutator becomes, it is concurrent, but what happens when the mutator becomes it's parallelized? Yeah, that's going to be a challenge. So in terms of VM evolution, I imagine if the shared memory, structured shared memory, where you have GC managed things that you can access in parallel for multiple threads, if that future comes to pass, eventually in 5 years, I think to be at the top of the performance game, everyone will want to re-architect their GCs, because the current way the GCs work are not set up for that. In terms of the language, yeah, that's probably a big new capability that might change how people write JavaScript. And to some of your point about non-resizable arrays and closed objects, I'm proposing those, so we'll see if that gets through. Yeah, hopefully, and this goes back to your previous question about the two groups of folks, because you can imagine if you are a scripter and you want things to just work in your experiments, you want your objects to be open. But we're now adding the other side of that to be more toward the big code bases, where you want the easier to reason about, harder guarantees that you want closed objects for. So the language is probably going to be more Java-like, which might be interesting, living up to its name for once. Yeah.
Hi. I had a question, but then I heard what you said about more academic research, and that made me react. I've done a bunch of research on dynamic analysis for JavaScript, and for researchers from an implementation standpoint, it's just a nightmare, right? Because you don't want to hack a virtual machine, because you guys are improving it in amazing ways every single day, and so then our patch is going to be madly out of date, and we're academic researchers, we can't maintain that. So then you switch to source code instrumentation, really, really hard to not break programs when you're trying to instrument source code in a systematic way. So this is a comment, feedback, or maybe kind of a question. Some kind of standardized interface for dynamic analysis, something like JVM-TI on the Java virtual machine. I know someone's got to invest in it. I can tell you that if even one of the VMs put out something like that was kind of guaranteed to work as the language evolved, I bet a bunch of academics would jump all over that and start doing a bunch of JavaScript research, just because the implementation of dynamic analysis is so painful. And I don't know if you all have ever thought about that. I bet it has practical use cases as well, right? I mean, JVM-TI is there and people use it for stuff, so I don't know. Is that something that could happen?
We have stubs for something similar, but I plan to delete. Sorry, yeah. We have stubs for something like that I keep planning to delete, but to your point, yeah, I think that would be a great research project to sort of collaborate on what does the shape of this look like? Like, what are the actual instrumentation points? And yeah, if we have them like prefed off by default and they're not too big a deal to maintain, I don't see why not. These are, and especially if we have a story for how they actually end up bringing value to people and how they can you can build interesting tools on top of them. I personally don't like taking off my Mozilla hat and not approving resources. I love the idea, and yeah, I think that'd be good. I get your point though about working on a production VM. Not a good sign. Not a good scene.
So we have about 1 minute left. I want to ask a question. This should be a quick one. Show of fingers. How many execution tiers have you deleted from your VM?
One of yours.
What counts as deleting?
You decide what deletion means.
Do I personally have to have done it, or does it?
No. Just over the evolution of your VM, how many execution tiers have you completely eliminated? 3. 3.
I guess 1.5.
No, it's at least 2.5.
Over my career.
Over the entire evolution, full cogen's gone, crankshaft's gone.
Over the entire lifetime of V8. Yeah.
I'm not sure how much the regex engine has been changed over that time.
Oh, I don't touch that.
It's at least 2.5.
0.
Okay, one last question. I think then we're out of time.
Are there any features that have significantly different performance for potentially idiosyncratic reasons across the engines? And I ask this as someone who primarily, I guess, like I'm paid to target V8. I personally use SpiderMonkey. I obviously have some interest in JS Core because of WASM bindgen stuff. Just like curious if there are any good examples of this.
SpiderMonkey sucks at generators, and we know that. But also, we don't think anyone ever actually uses generators. So we don't do anything. So we suck at them. Historically, we sucked at proxies. Manuel's proxy benchmark. We've gotten a lot better recently due to Vue.js. And V8 did a lot better at proxies. Oh, and only JSC implements proper tail calls, so...
So with that, let's thank our panel. So that concludes REBASE. Thank you all for coming, and thanks everyone for participating.